Get started. All right. Hello, everyone. Welcome to our workshop of Open World Vision this year. Um, yeah, I hope everyone is safe and healthy. The goals for the workshop is to connect people and exchange ideas related to open world vision and discuss new opportunities and challenges about this topic. And this is a hybrid workshop. We have online audiences here through Zoom. CVPR will record the Zoom and the presentation, and we release the recordings 3 months after the conference. Um, yeah, I want to introduce the term open world vision, but first of all, we should be aware that Walter proposed open set recognition 10 years ago, uh, more than 10 years ago, and Walter will be presenting soon. In that work, in Walter's work, he extended the traditional closed world training to open world testing, meaning that we care about the K classes and we train a model. And in the real world, real open world, during testing, we have never before seen novel objects or novel classes, and we should be detecting the novel species, right? So that is the open world testing, I would say. Uh, but later on, people realize that okay, we have open resources. Like from the open world, we can sample open data to augment the training data. Although the open data are not falling in the predefined K classes, we still can use them to help us train a more generalizable model so that we can do better job to detect the open set or unknown species. But now, now that we have modern AI agents or foundation models, then people would like to fine-tune foundational models and leverage open data to train better models. So I would say, oh, this is an open world vision. We have open training data and open testing scenarios as well. So the philosophy is to embrace foundation models, embrace open data, and solve real world problems. So maybe some people would say, oh, there's a data leakage issue, but is that a concern? As long as we solve real world valuable problems, it's not an issue to leverage open data, right? But even so, we still have interesting new challenges and opportunities. For example, we can study open world data imbalance issues, how to address corner cases infrequently seen by foundation models. And we can study why foundation models can still fail in some specific tasks or situations, and how to detect on what species or what training data or classes foundation models have not seen sufficiently well, so on and so forth. So we still have new opportunities and new challenges to study to do research. Um, Okay, I want to remind people that Tara Bolt proposed open world learning, the term 10 years ago. So the philosophy that they want to extend open set recognition by including another step. For example, if the model is trained well enough to detect unknown examples, then human in the loop or human annotators can annotate the detected unknowns and then keep training with the new annotated data, right? So we see, oh, this is a human in the loop annotation, but we have more to say about annotation, right? That's why I want to motivate open world vision through data annotation. I gotta say, in modern computer vision, machine learning based solutions, data annotation is the first class citizen. For example, for autonomous driving, we have autonomous driving experts collect the data and design annotation guidelines. For example, this is a snapshot shot from a new sense. We see how new sense um, annotation protocols design or define the classes of a bicycle and a truck. Um, then people hire human annotators to annotate the unlabeled data and use that labeled data to train expert model. But of course, we are in the AI era. We wonder how about we use AI to solve the autonomous driving problem. Oh, by the way, this paradigm of hiring human annotators to annotate the data is the de facto pipeline. And we have companies providing data labeling services like RoboFlow, Scale, we all know that. And for this year, we have a RoboFlow sponsor our challenges and the workshop. Back to the topic, if we use an AI agent, or here is the example, we use a foundational detector called a grounding dyno to detect a truck and a bicycle, and grounding dyno outputs the green boxes. And you see there's a huge mismatch between the green boxes, that is the predictions by foundational detector, and the expert annotations, which are the red boxes. We cannot say grounding dyno is wrong, so it still captures the truck and the bicycle, but it just doesn't align well with the expert annotations. Because experts have something in mind, like a safety concerns to define the bicycle and the truck. Because a truck, the huge truck, can have complex motions, and the people or autonomous driving vehicles should carefully handle the truck head and the trailer, right? And for bicycle, we don't need to differentiate between the rider and the bicycle, so we can annotate them as a whole thing. So from here, we see that AI is not enough, and we still need to annotate data to train expert model. And in other natural sciences or disciplines, we also have this issue. For example, in ichthyology, we study fish species. We have a camera under the sea to study marine science, so on and so forth. So people have long videos captured there, and experts will code the video or annotate the video by themselves. So you see, AI cannot do this. AI agent cannot understand the fine-grained details of the species. And also in ornithology, people have a trap camera to study biodiversity, so on and so forth. People have long videos, but they still code the video by themselves to understand what bird species are there. So you see, the whole procedure is intensive, tedious, and costly. The annotations can be erroneous, subjective, biased, and inconsistent among different individuals. So this motivates us to study, to think, can we develop methods to automatically annotate the domain data with domain expert crafted annotation guidelines? Of course, the philosophy should be embracing foundation models, embracing open data, and solve the valuable real-world problems. To stimulate this research, we have this challenge sponsored by RibbleFlow here. And we also have wonderful talks by fantastic speakers. So this is a schedule, and I hope people can enjoy all the talks and insights. Finally, I want to thank all the speakers, organizers, and advisors here, and especially RibbleFlow, which is the company graciously um, sponsor our workshop with financial support or prize. Um, yeah, that's it. So Nihar, please take over.
All right, thank you, Shu. First, I'd like to introduce our speaker for today, Walter. So while he gets set up, I'll give a proper introduction. Thank you.
Testing. Can everybody online hear me? Uh, testing. Where's the echo coming from? Oh, is it just yours? Okay, testing. Yes. Okay, we're good.
His research targets the fundamental problems of recognition and has developed many learning-based methods that break down traditional silos between computer vision and natural language processing. His work specifically explores open world recognition, extreme value theory models, and biological inspired algorithms, driving advancements across AI, machine learning, and human biometrics. Please join me in welcoming Walter Shear.
Great. Thank you for that generous introduction. Okay, so today I want to talk a bit about advances in post-processors for open set recognition. Yes, coming back to the open set problem, I know this is the open world workshop, but obviously open set remains a core of what open world is, and it's still not solved. So I hear a lot these days from folks working on foundation models that, you know what, we don't care about open world recognition anymore because like we solved it, right? We've got internet scale data, we've got these amazing transformer models. And so to convince myself that this was still relevant, I ran a little example experiment recently. First, I went over to Google's Nano Banana and I prompted it with the following. Create a photorealistic image of a highway where it is raining black droplets of oil. It's something that can't possibly happen in the physical world, right? This is kind of the injected novelty. And what I wanted to do here is see if this image would be parsed properly by other models out there, right? So I went over to ChatGPT. I uploaded the image I generated, and I asked it to describe the driving conditions in this scene, right? Thinking about applications like self-driving cars, right, which we heard about in the introduction. Here is the ChatGPT response. Let me read this. This is fascinating. The driving conditions look very hazardous. It appears to be raining heavily with poor visibility and wet reflective road surfaces that can reduce traction. There are dark, viscous looking droplets or streaks falling and splattered across the road, which could further obscure visibility and make the surface slippery. Traffic is present, and the low light, likely dusk or nighttime, combined with city lighting glare, adds to the difficulty. Overall, this would be a dangerous situation requiring very cautious driving or avoiding the road altogether. This is not a response any human would give this scene. Number one, this scene is obviously fake, right? Looks like an illustration. No, it can't pour oil, right, from the sky. This is not a driving condition, right? So the proper response would be something like, this is a fictitious scene. This is not something one would encounter in the real world. Please give me a real driving scene if you want me to assess the safety. Okay, so means novelty is still a pretty big problem here. So why is novelty such a confound? Going back to that paper that Shu mentioned in the introduction to this workshop, right? 15 years ago, we were talking about some of these same issues. Number one, we have to think about the training. We always have incomplete knowledge of the world at training time for open world domains, right? That's a big constraint. Yes, you can bring to bear all of the data that's on the internet, but that doesn't reflect the complexity of the physical world, right? We're always necessarily undersampling the physical world. The basis of all this, right? There's no basis from which to generalize novel data from known data, both of which are typically far away from each other in some feature space. I think that kind of hints at what's going on with the example I just showed you, right? There's really no basis for the model to assess that scene, right? Because I just created it from my imagination and had Nano Banana kind of render something and it added its own sort of flourishes. And so that's a big piece of that. And then finally, generation. New things appear in open world environments all of the time. This isn't restricted to object classes. Novel activities and interactions are also pretty significant confounds, right? Again, physical world, it's complicated. Okay, so coming back to open set recognition, we've known for a long time that there is a finite set of known objects and myriad unknown objects, combinations, and configurations. labeling something new, novel, or unknown should always be a valid outcome, right? This is an essential piece of any open world system. Obviously, if you're going full open world, it's not just about the novelty detection, which we care about in open set recognition. You're going to go beyond into some incremental learning regime. You're probably going to have a characterization step before that as well. But it turns out, right, we're still working on the open set recognition piece, right? The detectors are not perfect. There's been tremendous interest in this problem in the intervening 15 years since I published this paper, but we haven't quite cracked it yet. But that's good for us researchers because it's a fun problem. Okay, so over the years, two dominant paradigms have sort of emerged in terms of how one approaches open set recognition. The first approach would be the feature extraction approach. And of course, when we first started this work, neural nets weren't really the dominant way to do this, but of course now they are, right? So we're just talking about nets here. In the feature extraction regime, you're going to train networks that extract feature representations that enforce a better separation between known and novel classes when compared, right? So you see all sorts of novel training regimes being designed around this. There are lots of different examples of this in the literature from our sort of broader research group and others, the objective sphere approach, adversarial reciprocal points learning, class-specific semantic reconstruction, et cetera. The second approach, and what I want to focus on today, the post-processing approach. This provides novelty detection capabilities as post hoc add-ons to any closed set network. It processes extracted features, and this has a number of nice properties I'll talk about in a second. Examples would be the things I'm going to talk about today, but also some older approaches like OpenMax. And then again, if you look at the broader literature, there are a bunch of related strategies out there in anomaly detection, which of course is a very long history in the pattern recognition literature, out of distribution detection, open vocabulary object detection, et cetera. Okay, so what are some advantages of post-processors? Practitioners typically encounter the open set recognition problem during deployment, where networks have already been trained for some task. The post-processor method allows pre-trained networks to accommodate open set recognition without retraining. So that's a really nice feature, right? I can skip right to the novelty detection piece. I don't have to have, in many cases, elaborate training regimes. Now, of course, we in some cases do train these things, but they're much simpler statistical fits compared to training an end-to-end network. Architectures of differing training recipes incorporating open set recognition losses into training may yield wildly different results, right? So I may have some baseline performance for a network. I start tinkering with it to enforce this separation between known and novel classes, and all of a sudden the performance on the known classes goes down. That's not so great. We don't have that problem with post-processors, right? Because we're not affecting the base model's performance at all, which is good. Okay, so let's consider now three recent approaches that have come out of my sort of broader research group and specifically work from two postdocs that are in my lab right now, Steve Cruz and Ryan Rabinowitz. Both started their careers working with Terry Bolt, of course. So that's how they ended up in my lab. Again, we're going to look at three different approaches that have come out here, all post-processors, Postmax, which appeared at ECCV, the last edition of ECCV in 2024, Ghost, which appeared last year at AAAI, and CoStar, which we just published at ICCV in October. Okay, and these all do something slightly different, which is kind of interesting. And if you were very ambitious, you could actually use all of them together. Okay, so let's start with Postmax. What does this specific approach address? Basically, we're thinking here about optimal thresholds in our operational thresholds in open set recognition. We know that thresholding is a pretty essential piece to a novelty detection, right? I need to figure out, am I far enough away from known class information, right? That usually involves thresholding over some recognition scores, right? Most typically, we're thinking about thresholding over softmax scores or logits coming out of some network. And almost all approaches do this at some point. So if you think about this, right, if you're statistically minded, you recognize that the distribution of scores above the threshold naturally leads to a peak over threshold formulation. And if you dig into the statistics literature, you'll figure out that this is best modeled as an extreme value problem. So what we're going to do here with Postmax is create a post-processing refinement of the logits of the maximal class. And we're going to normalize logits by deep feature magnitudes, right? So we're actually going to look into some of the values coming out of the network to perform this normalization. And we're going to map them to proper probabilities using the extreme value theory-based generalized Pareto distribution, which formally fits this scenario. Okay, so let's look at some of the motivation for this. So we can consider the squared deep feature values from a pre-trained vision transformer. What we have here are basically sorted deep features of 20 randomly sampled images from class 990 of ImageNet based on increasing mean square magnitudes. And so to interpret this data here, if we look at the first row, oh, can you see my pointer here? This one over here. This is the row reflecting the known information, right? And we can see then that these square deep feature values are radically different when we look at knowns versus unknowns, which are the rest of these rows. So what I'm showing here in the next several rows are what we're considering to be unknowns. Basically, these are samples drawn from data sets that are not ImageNet, which is just reflecting the known situation. So looking at a bunch of different data sets, but looking at these samples that have been falsely classified, right, as class 990. Now, this is really interesting because if we're only looking at, say, the softmax decisions, we end up in this false positive regime. But if you look at these squared deep feature values, you can see, right, this distribution is radically different. We're getting much higher feature responses in regions where known sample activations are very low, right? So that gives us some intuition in terms of a normalization that can give us better separation when we have this setting. So basically, features from unknowns have on average larger L2 norms than those of the correct class, right? The knowns. And these large uncorrelated responses accumulate to give a high score for the class, but also result in unknown dataset features having on average larger L2 norms than those of the correct class, as seen in this plot. Therefore, dividing by the magnitude should enhance the separation, right? Which is exactly what we want if we want to be able to better apply those thresholds, right? Because if the scores are too close, we all know that the thresholding problem is really difficult. So all we do here in terms of the normalization is use the features and logits and divide by the feature magnitude to create a set for GPD fitting, right, which is our generalized Pareto distribution, fitting coming from the extreme value theory, guiding our peak over threshold problem, and get some probabilities, right? And we use these instead of the scores coming out of the network or even the sort of like raw logits coming out of the network. Okay, so we're going to come back to thresholding for unknown detection in a little bit because I'm going to introduce 3 different metrics, and then we'll look at the various performances of these different approaches we're talking about. Okay, so I'm going to move on and talk about the next approach, and it's called GHOST, the Gaussian hypothesis open set technique. Okay, so what does this one address that's different from postmax? Evaluations in open set recognition tend to focus on overall performance. That kind of hides some of the details of what's going on under the hood, especially if you have multiple known classes. Essentially, it's going to fail to provide insights into the performance across individual classes. So that's kind of what we want to address. This will affect the handling of unseen or novel classes and ensure a fair evaluation. So what this GHOST approach is going to do is form a hyperparameter-free model of deep features using class-wise multivariate Gaussian distributions with diagonal covariance matrices. And instead of using, again, say the softmax scores or the raw logits, we're going to convert this information into a z-score, which we'll use in place of those scores. And again, the idea here is we get better separation between the knowns and unknowns for applying those thresholds. So in general, this approach applies z-score normalization to logits to mitigate the impact of feature magnitudes that deviate from a model's expectations, thereby reducing the likelihood of the network assigning a high score to an unknown sample, which is what we don't want in open set recognition. Okay, so the training, what are we doing here? Basically, we're looking at the penultimate features and building these per class multivariate Gaussian models based on that information, right? So this is the information, right, related to the known classes. When input is from a class seen in training, each value in the network can be reasonably approximated by a multivariate Gaussian, and that, importantly, out of distribution samples would be more likely to be inconsistent with the resulting Gaussian model. So what we're going to do here is basically just do Gaussian fits on this data and get our parameters, right, our mean and standard deviation, and then we're going to store those. And we're going to use those then for a pretty straightforward z-score normalization. And it turns out, if you actually look at the statistics of this class per class information in the feature space, you can perform Gaussian tests for normality, and it's pretty consistent with normal distributions, right? So again, there's a different sort of way of thinking about it compared to the extreme value stuff, which again, if you're familiar with a lot of my work, it's been in that sort of regime. It's a little bit different. Okay, and that's all we really do. So for prediction, we run through those models which we've created during a training process, but again, very lightweight training process compared to what you would do if you were actually trying to do the feature learning approach for open set recognition. And then just renormalize everything, and then treat those again as sort of the scores that you're going to use. Again, we'll come back to thresholding to see how this actually works in a little bit, especially considering the per class nature of this, which is pretty different from a lot of evaluations that just aggregate all of the classes and do this globalized evaluation. Okay, one more to chat about before we look at those results. CoStar, right? So this is our most recent post-processing approach, which I mentioned just came out at ICCV last year. What is this one addressing? Okay, coming back to the literature, there's a really interesting paper that came out a few years ago, authored by Tom Dietrich, which came out of the DARPA Salon program, familiar with some of the sort of background research in open world learning that a lot of folks have been talking about recently. Tom and his co-author introduced what they called the familiarity hypothesis. And they argued that networks are detecting novelty by the absence of familiar features. And that seems generally true based on a number of experiments that they performed. But there still is this lingering question in our minds about this. Why do approaches implicitly focus only on the familiar features? What's going on there? Can we actually dig into this a little deeper? And that's what we did in this paper. What we did was introduce a new attenuation hypothesis that explains what exactly is going on here with the familiarity hypothesis. And I'll show you some data to support this, but basically small weights learned during training attenuate features that serve a dual role, which you really, really want for open set recognition. They differentiate between known classes while discarding information useful for distinguishing known and unknown classes. So this attenuation is throwing out a lot of information that you ordinarily would want to keep. But of course, right, since these networks aren't inherently designed for open set recognition, this is a missing piece of the puzzle. Okay, so let's look at some data to substantiate this. Okay, so in this one, the first row, these are the sorted class weights for a particular class coming out of ImageNet. And then we can look at the original feature values, right, before we apply those weights for a sample from this same class, 389. This is our known row down here. This is the second to last row. And then the last row would be the feature values from a sample drawn from the NINCO data set, where again, we sort of confused it with this known class, but it's really an unknown sample. Now, when you look at this before the weights are attenuated, there's a lot of information there, right? Which is pretty interesting. If you look at then the Hadamard product between the weight vector and these feature values, all of a sudden you see these big regions of white where this information has been wiped out, right? This is what we're calling the attenuation. And so all of a sudden we've lost that information. So for computing scores based solely on the post-attenuation data, we've perhaps lost a lot of discriminating information. And that indeed is actually the case here. So why exactly is this a problem? For this particular example, the average logit for the known samples is 8.959. Well, for the unknowns, it's 8.143. They're almost the same, right? That becomes a problem too when you do the softmax calculation, right? These things are going to be very close in score space. So if we preserve the pre-attenuation information, though, and go through this CoStar process, which I'll talk about in a second, the score situation is drastically different. For this same setup, 0.647 for the knowns and 0.369 for the unknowns, which means we have really good separation for applying our threshold, which is exactly what we want. So again, to sort of summarize here, the key thing, features which help distinguish known and unknown classes are being attenuated by classifier weights. Okay, Skip that because it says the same thing. Okay, so in the approach, all we're going to do is preserve that information, but we're also going to keep the post-attenuation information as well, right? So you get a concatenation of both. So you can imagine having some pre-trained network. We're going to have a feature vector before we apply the weights, which is going to be F, and we're going to preserve that as our pre-attenuation information. And then we have our weight vector, and then we can take the Hadamard product of both of those, and that becomes our post-attenuation information. All we do is concatenate those together, and that becomes the vector we're going to consider as we compare CoStar similarity to actually get our score. We can also include this lambda term here, which is actually the logit information if you want that as well. That's more information you can include. So that's kind of a three-way piece of information or a string of information. And again, we can threshold these, and we'll talk about the thresholds next. So again, we found this to be, again, highly effective because we bring that information back in after we've lost it. Okay. Okay, so the final piece here, experiments. How do we measure these things? We know in the literature that traditional metrics, right, traditional object recognition metrics are pretty prevalent. Area under the curve, false positive rate, 95%. The downside for using these for open set recognition is that they're designed for binary problems. What we really need is more nuance for open set recognition because we want to account for knowns and unknowns separately in some cases. It's important to understand as we mitigate unknowns, are we impacting the performance on the known classes, right? We fold all that information together in one of these more standard metrics, we may be losing some sense of that, or we don't get any sense of that. So I'm going to talk about three newer metrics for doing this: the open set classification rate, the operational open set accuracy, and the coefficient of variation of correct classification rate. And we'll also look at the performance of these three post-processors compared to some other post-processors that are very prevalent in the literature these days. Okay, so the first metric is actually a bit old at this point. Terry Bolt published this back at NeurIPS in 2018, but it's still quite useful for a lot of what we're doing here, the open set classification rate curve. What this one does is plot the balance between correctly classified known samples and falsely accepted unknown samples, right? So we account for these things differently. So you can see the correct classification rate becomes the y-axis of the curve, and the false positive rate mapping back to the unknown samples is the x-axis of this plot. If we're, again, considering our post-processors that are looking at things not at an individual class level like Ghost does, so this would just be Postmax and CoStar, we can compare them against a number of common post-processors in the literature, especially those drawn from the out-of-distribution or out-of-domain literature. And so that would be something like Scale, NNN Guide, MaxLogit, MSP, etc. We do a lot better. And again, this is sort of intentional design specifically for open set recognition. Out-of-distribution detection is often a little bit different because you still are sort of in the known space in many cases. So it's not terribly surprising that these are doing a little bit better. But again, the key takeaway here is this is a better metric for looking at it because we've correctly sort of separated the known classes and the unknowns, and we're looking at the different aspects of them. Okay, that's not the only way to do it. In the Postmax paper, there's an interesting observation in that if you look at the literature in open set recognition, there's a fundamental problem in the evaluations in many papers in that the choice of the threshold is kind of an optimal threshold. It's been tuned on the testing data. That's not good. That's essentially cheating on this problem. So what you really want is to figure out a way to pick a good threshold on a validation set and incorporate that back then into the formulation in evaluation. So this operational open set accuracy characterizes things by selecting an optimal threshold specifically on a validation data set and then reporting the resulting open set accuracy on a test set. And again, breaking things down, right? So we have some separation between the known data, right? Thinking about correct classification rate, and then the unknowns, and that's factored into this unknown rejection rate, and then computing the overall open set accuracy by looking at both, and then you can sort of plot that against the unknown rejection rate. And again, we can look at two of our post processors that are looking at, all of the knowns together, Postmax and CoStar, And again, a lot of these approaches that are post-processors from the literature, and again, putting them all on sort of even footing, right? Again, doing this validation process to get the thresholds. And these approaches are pretty good. And then finally here, we can look at the coefficient of variation of correct classification rate. So this one's really interesting because this breaks down things at the class level, which again is largely been ignored in a lot of the work in open set recognition. So as we select a false positive rate threshold, we would expect to sacrifice the correct classification rate uniformly. But if we look at a metric like coefficient of variation, it shows that many post-processors eliminate known classes unequally. In some cases, entire classes are rejected just to achieve a moderate false positive rate. That seems really bad, especially if some of those classes are mapping directly back to your task at hand, right? We want to make sure that we sort of still include those. So again, this is a way to look at this at a per class breakdown. So again, this is the kind of a setup that Ghost was designed for specifically. So you can see that like Ghost is handling the situation really, really well with a low coefficient of variation at very low false positive rates, which is exactly what you want. While a lot of these other approaches, again, are sort of not designed specifically for that per class breakdown, and you don't have the kind of performance that you would want. Okay, so let's summarize what we've learned here. What are some takeaways? Number one, the post-processor approach I think is really attractive because it really shifts us away from expensive computation, small-scale data, and traditional metrics, right? We can bolt these things onto basically any arbitrary network. We've done this, right? Vision transformers, we've done this with more conventional sort of like older school convolutional neural networks, right? Whatever you want, you can sort of like put this into, right? Even very large transformers. And again, you don't have that daunting challenge of retraining. That's good. What's also neat about these two, they can handle large data, right? Because again, a lot of these things are being tuned in their training phase on just, are being they're processing through a statistical fitting process, right? That isn't a traditional neural network training regime. And so that means, again, you can sort of process more data. And then we're also arguing in a lot of this work, again, we're not looking at the right metrics. We need better metrics to really sort of pick out what's going on between the knowns and unknowns. And in some cases, looking at what's going on a per class basis. Okay, other things. Improvement over good closed set classifiers, right? There was an argument from the Oxford group a few years ago that all you need, right, is a good closed set classifier. It turns out a good post processor is actually better than doing that. Three, we want to operationalize open set recognition, right? A lot of these metrics, again, are designed to help practitioners, right, with real problems in the field, right? Things, again, like autonomous driving. Want to look at real settings, a lot of difficulty there. But again, these things are designed to help us understand the problem setting and actually solve some of the problem. And finally, system-wide thresholding has unequal effects on known classes. Again, I think this is something we want to dig into deeper, right? Like sort of one threshold doesn't rule them all. The Ghost approach is really nice because it's breaking things down using these per-class Gaussian models and then performing a normalization based around that, right? To get that better score separation on a per-class basis. I think all of that is pretty essential. Okay, with that, I will wrap up. I just want to acknowledge again the co-authors on this work, Steve Cruz, Ryan Rabinowitz, two fantastic postdocs in my group who came out of Terry Bolt's group. And Terry Bolt, of course, a major contributor to all of these approaches, who unfortunately could not join us today because he's relaxing on vacation somewhere. Okay, with that, I'll take questions. Thank you. I know it's early, but surely there's a good question.
Maybe I could start off.
Yeah, please.
So, in the spirit of deploying this for real practitioners, so one of the issues that we have when we deploy machine learning systems in the real world is there is no real val set or real train set. It's sort of a stream of data.
Yeah.
So how do we reconcile, the kinds of things that you're thinking about with this? And then maybe a related question is, the real world has natural distribution shifts, and obviously, the threshold that you pick on your validation set may not hold, if you sort of run your model in the wild for, a couple of minutes, a couple hours, a couple of days. So how do you sort of reconcile all of this?
Yeah, okay. So these are two good questions. Let me start with the second one. So we have another vein of work looking at what we call nuisance novelty, which would be kind of these domain shifts in many cases. So a really common confound for open world learning systems. Agent is in the wild, right? It has a good sense of what the known information is, like in a specific distribution. Something changes in the environment, right? The known data are still there, but there's been this distributional shift. That's not novelty. The agent should flag as novelty and count as something separate, right? It should adapt to that. So what we've been working on is actually nuisance novelty detection, right? So this is kind of a novelty characterization process that helps us mitigate that issue because we'll know to ignore it, right, and just move on. Or perhaps again apply some kind of normalization to get it back to the domain that we're interested in. The first question is more complicated, right? Because as I pointed out at the beginning of this talk, we're always undersampling the physical world, even if we train on the entire internet, right? So that's a limiting factor with these validation sets. So I don't know if I have a satisfying answer, right? Again, I want us to use validation sets because if you're not, you're cheating, or you have suboptimal performance, right? And just out of the box. But I think we need to think hard about what is a good representative sampling to do this, right? And again, this is the sticky question about generalization. Um, I don't, yeah, again, it's hard. That one's hard. That's where I'll leave it. Yeah, sure.
Thus far. This particular domain that you're speaking is a bit new to me. But I kind of wanted to revisit sort of your initial example there with the oil field growth and some of the sort of novel experiences. So, given current events with Ukraine striking Russia's oil environment, they actually did have a day where it rained.
I knew somebody was gonna point this out.
More. You've got examples with like tornadoes going over lakes.
Yeah.
Rain, fish, rock slides, and mountainous areas where rocks fall the roadway. So, for instance, with autonomous driving situations, which you brought up, we find examples where we do have areas that are essentially so far out of domain, the models working in those environments don't know how to handle them, which unfortunately with like Tesla has led to Teslas driving at freeway speed into semis that are overturned on their side, or driving through, hazardous accident environments at full speed. Can you speak just like
Yeah. This is a good question. So you're absolutely right. So as a fact, it has rained oil, though not in this exaggerated, right, like fantasy depiction that I'm giving you. So in my defense, I created these slides before that was reported in the news. At least the one I read was Iran, right? Like these strikes on Iranian oil facilities. I did see some like open source intelligence videos where it was like a few droplets, and like when you zoom in, it's like clearly oil. But it's totally different in terms of that depiction from what I'm showing you, right? Like again, a good AI system should note like this is not something, my example, that could appear in the physical world, right? Because this is an illustration, right? It's like artistic. There's no way you could get enough oil in the atmosphere where you'd have these giant drops, I think anyway, right? That said, it's still interesting. Yeah, this actually happened. So I think this is a good case, and not inconsistent with what I'm presenting here for the full open world recognition system, right? Where it's like detect novelty, right? So the system could say, this is something new, right? If it's observed over and over again in time, we probably want to have a characterization step that notes that, right? And starts to figure out what is going on here. This is a new state of the world, right? Raining oil. Build that into the model in an incremental learning step, right? So accommodate it. So I think the key issue here in my example is that there's like a problem here in terms of the lack of novelty detection. There's nothing wrong with detecting that novelty and putting it back in your model if you're seeing it over and over again. Does that make sense? That's a really good question. Anything else from the audience? I know it's early. Yes, there is one in the back. Yes, Alice. Oh, I didn't see you back there. Hey. Ooh, a quality metric detect. So yeah, so again, coming back to what I was saying to the first question about nuisance novelty, if you have that piece, the answer is yes, because a lot of the nuisance novelties we've observed in the wild have been image quality problems, right? There's been some sort of like hue shift in the image. You can imagine like a sensor starts malfunctioning. There's all this noise. And again, if you're accounting for that as a specific type of unknown and correctly detecting it, then absolutely, like this is a big piece. In fact, we have a paper under review right now looking at that, which I can share with you. Great. Anything else? No, great. Thank you, everybody. Oops, wait, I think I need to stop sharing. How do I stop sharing? Oh, maybe it died. I think it died. Am I? Or no, I'm still. Oh wait, hold on. I think if I close Canva, now I get. Okay, I get this back. Stop sharing. There we go. Okay, you should be. Oh, and let me stop.
All right. Hope everybody can see my screen on Zoom and hear me.
Put on your camera.
Oh, yeah.
Oh, did I not have that? No, that's why we had it.
Okay. Oh, yeah. That's what.
Lights.
Hold on.
Our next speaker today is Satya Akar. He's an assistant professor of computer science and software engineering at Auburn University, having previously served on the faculty at Oklahoma State University. Dr. Akar's research focuses on open world learning under limited supervision. Rather than relying on massive annotated datasets, this group builds intelligent agents that leverage prior knowledge and structural context to reason about the visual world. His work advances self-supervised learning and common sense guided perception, applying these methods to data scarce domains like active vision, genomics, agriculture, and security. Please join me in welcoming Satya.
Hi, everyone. Morning. So I'll be presenting about open world human behavior understanding through active event perception. I'm an assistant professor, like Nihar said, at Auburn University. So at this, I wanted to first put in a clip from Iron Man to motivate why open world behavior is interesting and why it's hard and how we have human robot interaction in the wild is hard. But then I was attending a talk yesterday about Gemini Omni, and I was like, okay, why don't we just use Gen AI to generate a situation? So imagine a future, right? I mean, it might not be the future in this clip right now, but imagine that you're trying to cook for the very first time in a dorm room, right? And you're following instructions, and it says to flip something, and you're just not sure. You panic, and then the eggs start burning up, and the whole thing is filled with cloud, right? With smoke, right? To avoid this, you might have a future where there's intelligent agents sitting, next to you, maybe a robot that's assisting you with it, and it needs to help you complete your task without you panicking and burning down your dorm room, right? So for that, you need to understand what they're doing, what's their overall intent, what are the objects, actions available to them, and so on. And current computer vision systems do that. And as you see, the person changed, but the context still remains, right? So that's a problem in open world generation, if you want to think about it, right? So current computer vision systems can, recognize these objects, recognize actions, and sort of, help you tag what you're doing wrong, especially if you have an AR system and so on. But if your dorm room is burning down with burnt eggs, you don't really just want an AR system to say, "Hey, it's smoke, do something," right? You want it to actually help you do it, right? Solve it. So you're struggling, you forgot your pen, your arm comes in, now it disappeared magically, but it has to stay in next to you in the real world. So helps you complete this task, right? Without you panicking, not burning your dorm room down, and you're good to go, and you actually have breakfast to eat and get to class and so on, right? So it's a pretty complex problem, especially when you consider the open world, and with the questions that was asked in the previous talk about novel actions happening, how do you situate it, and so on. Humans do a remarkable job at it, right? So we can react to situations mostly, especially if you're not panicking. But we do this by organizing our life and things into events, right? Events are mostly how we organize our experience. So whenever you see an event, you're watching the YouTube video, you're attending this talk, this workshop, you're organizing this into events. And in psychology, you know, events have a very specific definition. So you have a spatial and temporal location for your event. There's a clear start, a clear end, and a clear location of what you do it. And when you do segment your events, you also tend to characterize it, right? So you go and say, hey, who's doing this, right? What are they doing? Why are they doing this, right? How are they doing this? Where is it? And when is it, right? So you looked at that video, you know, you might notice that the person's playing a guitar and they're probably in a road, right? There's people in the background, so it's probably a restaurant. They're doing this because they're a street performer and they want to, you know, entertain people and so on, right? So a small clip, you will tend to situate yourself in that particular region. And if you just dig a little bit deeper into what you just did, you're doing several things, and that's really hard to do, right? First is, you know, you're understanding what you're doing right now, right? So that's action recognition, right? So if you look at egocentric videos, you know, you have a point of view of the person working, cooking, and you're recognizing the current action, right? You're just saying, hey, they're putting something into the stove, they're cooking, and then it has fine grain or coarse as you want, right? And then implicitly in the back end, you're also doing what are they going to do next, right? So you're seeing that, you know, they are taking cereal, they are pouring cereal. So you're in your head, you're forecasting, you're predicting what's the next step they're going to do. So you're saying that, hey, they're probably going to take a bowl because then they're going to take the milk and they're going to do certain steps. Now, dig a little bit deeper into why you did that. You create a partonomic structure, a hierarchical structure of that event, right? You're putting yourself in their shoes and saying that, hey, the overall task that they're doing is making breakfast, right? And within breakfast, they're going to make coffee, they're going to make cereal, they're going to make a sandwich, right? And then within cereal, making cereal, they're doing these different tasks, right? You know, taking a bowl, pouring milk, or taking milk, taking cereal, pouring milk, and so on. And if you break that down even further, right, you get even more fine-grained actions, right? And at some point, you end up with atomic sub-actions that you compose and so on. So just understanding that particular video would make you do all three of these things. And then that, in turn, can help you assist that person saying that, hey, if I make a mess, I'm going to need something to clean up. So if you are assisting that person make, you know, the breakfast, you do all this situated reasoning, and then now you can help them without them having to prompt you for saying, hey, go get me a napkin, go get me a knife, go get me a bowl, and so on, right? So that is sort of where we want to go towards, right? We want to have proactive, immersive assistant, you know, agents in the wild. Now, how do we do this, right? From the vision perspective, right? There's different ways to, you know, solve this problem. A lot of it involves assigning semantics to the videos. The obvious one is supervised learning, right? So, you know, you have your assumptions is that your data distributions stay the same across training and testing, right? You take a supervised learning approach, transfer learning, semi-supervised learning. Then you say that, you know, during training, I have, you know, some semantics of someone taking a tomato or cutting a tomato. And I assume that during test time, I have the same distribution. Say the label, the video, the lighting, almost everything remains consistent, right? Then, you know, you have the generalized zero shot learning where you slightly open this world, right? You acknowledge the existence of other labels other than the ones that you actually see, right? So here, you know, during training, you have some samples, right, for taking a tomato, cutting a tomato, just to stay with the kitchen theme, right? But you also acknowledge that there does exist other actions, right? So you can have take pepper, cut pepper that might come up during your test time, right? Now, you know something exists, but you might not have you know, data for you to train a supervised learning model on that, right? And we've seen a lot of success in zero shot and generalized zero shot learning. Now you expand that even more and you get into a known world, right? So this is sort of where we are with foundation models and LLM driven, you know, reasoning and so on, where you train on a very large amount of data, web scale data, and you pretty much try to make the test set your train set, right? So you try to get as much data as possible and then make the open world a very big closed world, if you want to talk about that, right? So then, you know, you during training, you have these labels and then examples come from seen and unseen. And you sort of hope that you generalize or you you learn enough of the patterns that you generalize to new labels, right? And then we come to open world learning, where during training and testing, you don't really know what data that you have. You don't know what you're going to encounter during test time, and you really want to generalize both during learning and during test time, right? Because you want to learn enough patterns and to guide your model to recognize something new, but also try to label it as with specific semantics that you have. So during training, you probably just end up having some search spaces, right? So you know the existence of certain objects, you know the existence of possible actions. Again, this could come from an LLM, could come from knowledge graphs, and so on. So these are, all possible actions and objects that can exist in the world. And during test time, you want to find the combination of actions and objects that just occurred in that video, right? And then, of course, you want to situate it within your hierarchical event and somehow use this knowledge to assist the person in an embodied world. Now, what makes this really hard is that there's an unknown composition, right? So you don't know what's the combination of actions and objects that's going to be there. So, for example, you could say that someone is scooping peanut butter out of a jar with a spoon. That's common. But if you don't have a spoon, I've seen people do that with a fork, a knife, their fingers, right? Everything. So that's still scooping peanut butter out of a jar, right? But there's different objects there. Now, you can possibly try to do this with captioning, but then again, you're gonna encounter new objects that's not in your training vocabulary. Generalizing beyond that is hard, right? Second one is partial observability, right? So we can't always assume that the person's always going to be within the view of the camera all the time when they're cooking and then doing and so on. So you have to have some way of navigating the space so that everything that's needed for you to take an action is within your view. That's where the active vision comes in, right? And then, of course, when you move around, the viewpoint and the perspective changes, right? So you need to understand, have a persistent state, right? So to me, the laptop's to my left, so if I move the other side, the laptop's going to be on my right. I need to understand that spatial change so that I can still continue to assist that person, right? And lastly, predictability in actions is hard. Humans are random. We tend to do things, especially, when I'm cooking, I jump from dish to dish and it's like, it's chaos in there, right? So there's uncertainty. We can't really expect predictability in actions for everything, right? So we need to understand the causality, understand whether you can do certain things, you cannot do certain things, so you can identify mistakes when they happen and sort of prevent you from making mistakes that's irrecoverable, right? So the key thing with open world learning and at least in videos is to tackle this evolving semantic space, right? So I'm going to talk about three things here. The first work is our work published at ICCV last year, where we were trying to do similar in spirit to Walter's talk about post-processing of pre-trained models to tackle this evolving space. So we have made tremendous progress in VLMs, video LLMs, and in doing zero-shot recognition. So what we did here is called PROGRESS, a probabilistic jump diffusion for open world recognition. So instead of just blindly searching over a known search space, like for example, you have 10,000 activities that can occur in a video, instead of just brute force searching using a multimodal LLM, can you be smart about how you navigate this search space, right? So what we do is something called jump diffusion, where we have two phases, an exploration and an exploitation phase, right? Exploration is where we construct the search space, right? We don't assume the presence of activities, right? We have a list of objects and actions that we can sample from an LLM. In this case, we use ConceptNet, and we have a way to set up the search space and assign prior probabilities to the validity of actions, right? And then we use the VLMs to actually take the video as input and provide a likelihood score, right? This gives us direct video evidence and try to use the training knowledge from the VLM to provide some likelihood scores. And then we balance this out to use the prior to look for certain probable actions and activities that can occur. And then, we refine it at the end, right? So why this matters is that, one, it reduces the number of costs that you make to the VLM. Second, if you just look at the feature space or the semantic space of LLMs, it's really hard to distinguish between closely related terms. Like, put salt and take salt are very, very close to each other. And, and when you cluster all these features, I'll actually show you an example when we see it. Some of the closely related or placed embeddings in the search space are totally not related at all, right? In the LLM space. So that means that your VLM can get confused between certain closely related actions, and you might have false positives, all right? So the prior knowledge allows us to avoid going into areas that we know don't make sense, right? And just look for high likelihood areas. So how we do this is through jump diffusion, like I said. So you have your video goes in through a video encoder, right? And that gives you a likelihood, right? And then we have our concept net that gives us our search space and helps us navigate this by avoiding areas that don't make high semantic sense, right? Like, throwing something in a kitchen and so on. So this guides, well, hopefully that doesn't happen, but sometimes it does, right? Especially if you're dealing with a 5-year-old or your puppy in the kitchen, right? But, that guides your exploration, and we want to use this to sort of go to high density areas and sample more from there and avoid these low density areas based on semantic probability, right? So if you look at it, this is sort of a search space for EgoVLP, one of the first foundation models for egocentric videos. And what you're seeing here is a jump diffusion. So you have a proposal that some of these actions are being proposed, and the blue part is our exploration based on priors, and the red tackles the ones that are close. I don't know if this is visible, but as it gets to the blue part, you'll sort of see that it's all over the place. It's like put honey, cut, using a knife and so on. As you get into the red part, which is using the VLM's likelihood to fine tune it, it sort of learns to search around areas based on keeping the high likelihood think, which is the take, and then tries to go through different combinations of objects until we get to take fork, right? So this allows us to sort of define a search space, right? If you know it, great. If not, you can use LLMs to do a completely open world and do it and search over it. So how does it do in terms of evaluation, right? So in a known world, right? So we know what activities exist. So we compare against just foundation models like EgoVLP, Lavilla, just doing brute force search, right? And also against prior neurosymbolic models, these two are from our group that did not use VLMs, just use video features to just assign labels and go on. We sort of see that just brute force search gets you pretty far, but then it just gets stuck, right? But if you learn to avoid areas where there's low semantic probability, just using the same base VLM, you can get a significant jump in terms of getting the activity performance, right? And of course, if you look at exact matches for the actual activities, that is still pretty low because, how would you evaluate, a prediction of, put salt versus add salt, right? So they both semantically are doing relevant things, but they're just, phrased differently based on annotated goals, right? And we evaluated across 4 different data sets, all egocentric videos, and we sort of see consistent gains over just base VLMs, but just by searching over a defined search space without going into low probability areas. Now, of more interest is probably this table where we don't have this predefined search space, right? So we just prompt an LLM. So L2 basically says, I know the domain, I'm cooking, right? So give me all possible objects that can exist in any kitchen, and what actions can I do with those objects? So we prompted Gemini to get this search space, and that resulted in around 37,191 possible activities that can exist, right? And then, with our sort of progress search, you can do like 15, it only sample 1,500 out of this 37,000 probable, activities, and it still was able to outperform, the base model, whichever model that you use, it did outperform them or get very close. Now, L3 is the completely open world. So we don't know the domain, right? We just said to Gemini, hey, just give me a list of 1,000 objects and a list of 1,000 activities or actions that you can do with it. And then that resulted in about 195,000 possible activities that can, you can probably do with this, unique activities, right? And then you use this to search over our known vocabulary that you have, and with around 5,000 calls, we can get better performance, much more semantically meaningful results from the same base VLN. So some lessons that we learned in this paper is that VLNs are really good. They can match phrases with the video evidence, but they do get stuck in traps based on semantic similarity within the LLM's semantic space. So if you can learn to avoid this, then it does help you get better recognition performance. But then you still need to have additional context, and that helps in narrowing this down in a much more reasoning-based method, right? So then that will sort of let us to see, can we extract the hierarchical structure in events? Because if you're pouring milk, you would have taken milk at some point in this video, right? So then if you have that additional context, then that will help us understand the causal structure between activities, right? And that sort of helped us define this idea of event partonomies. Again, this is not something that we defined. It's existent in cognitive science literature. It's been widely used in instructional or procedural video understanding. But we were tackling the problem of how can we extract this event, not just use this event, right? Event structure. So again, we went back to our inspiration from cognitive science and came up with this parse or predictive learning architecture. So we have a multi-level predictor. So at each level, right, there's a predictive network. It could be, we use an LSTM because it was really easy to train. Transformers do equally well. So you have one level of predictions. It predicts the features from the level that comes before it. So at L1, the raw frames of the videos go in. For every frame, you predict the features of your next frame that you expect to see. Any deviations, right, tell you that you don't really know what's happening here, right? So there may be something new. So if your predictor model has a good internal model of the event that it's modeling, then it would have low prediction error. If the prediction error goes up, then it's something new, right? So for example, for every level, if you just feed in the raw video data, right, what you see here at the bottom is the prediction errors, right? And as the model keeps predicting and updating its internal state, you'll see that the prediction errors are lower. And when there's a transient increase in prediction error, then we mark it as a new event that's happening, right? So you do this at every level, right? So this is showing at the bottommost level. But if you do this at every level, so at L2, you take the internal state of L1, right, and try to predict what the event state or the abstraction is for the L1 predictor, then you get the prediction errors at L2, right? And if you take the states of L2 and start to predict it at L3, you get this sort of hierarchical structure. And if you try to extract the transient increases in error, you will end up with event boundaries at different hierarchies. Now, the need for doing this in a unified way is that a partonomy structure like here requires you to have nested events, right? So make breakfast is completed only by having all three of these events within them. So you don't really you need to make sure that the start and end of all of these events are within the bounds of the event that's above it, right? So this nested structure is really hard to get if you do predictions at different hierarchies without considering how they evolve by themselves. So if you look at what parse did, we evaluated in two different tasks. One is hierarchical boundary detection, right? So, trying to predict the boundaries at different levels, sub-actions, actions, activities. And we sort of see that, compared to baselines that are naturally conducive to doing this, like, hierarchical clustering, right? Or doing k-means at these feature level. Having, this predictive learning does help in getting good boundaries that are more importantly self-contained within a hierarchical structure. Now, these numbers might not make sense just out of context, but this qualitative results might help, right? So you sort of see that this is our ground truth partonomy, the two-level partonomy on breakfast actions data set. You see that you have defined grain events are completely contained within the coarser grain events, right? And that is also the case with ours when we do this. And it has a really neat way of building this graphs out of your streaming data, right? That's there. Now, again, while we were building this, we were also concerned about, what happens if the person moves out of view, like in this example, you'll sort of see that the person is moving here and then they'll go out of view, come back in, and it'll be hard to sort of build this even structure if you're trying to get a robot to help this person, within their homes and not just looking at videos. So, the real world is dynamic. How do we deal with occlusion, right? So if your camera is active, you can actually reposition your camera so that they're always in view and you can track them and make sure that you get every aspect of the event that you're doing. But then again, we're dealing with an open world and we don't really want to go back to supervised learning or just using reinforcement learning to train a model to track a person, because you might have two different people in the room where you train for just one and so on. So where does supervision come from for active perception, right? So we sort of saw this idea of predictive dynamics providing cues for temporal segmentation. What we also saw was that if you predict at the spatial level, it actually gives you cues for uncertainty in areas of the frame where prediction errors are higher. So if you follow wherever the prediction errors are higher, that gives you cues for where the actual event is that you want to follow. And if a person goes out of room and it's just the background, the prediction error will be low because nothing is changing, right? This sort of gave us some idea on how we can use prediction dynamics as a way to track and build a person's event model. So what we did was use the predictive learning idea as supervision for reinforcement learning models. So if you look at this, the spatial location of the higher, prediction errors. So that became the reward for a reinforcement learning model. So we use DQN to minimize the error taken by the predictive model by picking an action that would minimize this overall prediction dynamic error. And while that sounds really simple, it gave us like really nice outcomes, right? So here we tested it on a Locobot, and you can sort of see that whenever my student's moving along, the prediction error changes and it actually starts to track the person. This is the egocentric view from the robot. These are the prediction errors. And these are the key frames from event changes that happen. So we can build this hierarchical event structure in a streaming video on a Locobot, and the whole thing runs on CPU on the Locobot without having the need to access a GPU or stream it out onto a GPU, right? And the idea was simple, just minimize the prediction errors, but it learned something pretty cool, right? So here, my student Joe is pretty close to the robot, and it learned to step back without having us to train this behavior. So it steps until until he's completely within the frame. And note that the predictive learning model doesn't know what a human is or is not trained to give any sort of cues for keeping the human fully in the frame, right? So the predictive dynamics allowed the model to learn this behavior on its own, right? So there's some powerful cues in predictive learning that we can possibly leverage to build open world active agents. Okay? So in summary, right? So we sort of have this thing that open world behavior requires a lot more than just recognition, right? It needs systems that can reason over these evolving semantic spaces, right? It needs to be able to infer hierarchical event structure. It has to be able to predict and adapt under uncertainty. And I heard like from the Bitter Lessons workshop yesterday that the next better lesson is agents that can learn continuously, right? They're going to scale and survive more than those that don't, right? So perhaps that's one thing that we could learn for open world learning in terms of active vision as well. So can it adapt and predict and adapt under uncertainty? And of course, you need to be able to acquire additional information by actively manipulating your geometric structure of the camera so that you can get better and grounded results, right? So here we look at in our lab at least that open world understanding is a structured inference problem, right? And hierarchical event representations provide a path towards the scalable event cognition in this open world paradigm, right? And I'd like to thank all my students that worked on these things that I presented, and of course to the funding agencies that funded this work. Right? Happy to answer any questions that you guys have.
Yeah, kick us off.
Yeah.
This is great. One thing I've been interested in recently, known objects, but novel like interactions or configurations. It looks like you've looked at a little bit of that.
Yes.
Do you think that's a significant confound or something we should be looking at more, or is it really just like the next step of like novel activity, or is it some combination of all these things?
So it's a combination, and we have been looking at affordance-based interactions. So you can have the same object being used in multiple different ways.
Exactly.
Yeah.
Right?
So we have been looking at that, and we've seen with similar ideas like progress that prior knowledge plays a role in trying to identify the known uses, especially when you're having the agent do it versus observing someone do an action with an object. Right? So the recognition and the usage of the object by the agent itself are two different problems that we've sort of figured out, because mostly in terms of contact prediction, where do you grasp an object? Like, for example, one of the things that we're working on is like, if you ask an agent, like, give me something to cut with, right? You don't really want the robot to give you the blade side to you, right?
Yeah.
But you wanted to give it the handle side first, right? So that in itself is a problem, because now the agent has to reason, I need to pick up a knife because I can cut with it, but do I pick it up with the blade because I have to give it to a person, or should I take it by the handle because I can use it by myself, right? So that adds another set of problems within this affordance-based reasoning. And our neurosymbolic approach before Progress did try to do affordance-based action understanding. But there's a because humans are naturally like perceptions, right? Random in how we do things. Like my advisor always said this, right? Is it a chair because you can sit on it, or is it a chair because you do sit on it?
Yeah.
So that changes the nature of how we perceive things, and that might be another level of challenge into that. Hope that answered your question. I went on tangents.
It's like, yeah, a lot of cooking is like ad hoc, like you mentioned,
Yeah.
right? So it's like there are a lot of objects that are known that are in like strange configurations,
Right,
right?
yeah.
Where it's like I have one, like kitchen implement, like it's like, oh, I'm gonna use the spatula as like a rest for this spoon, right?
Right.
And all of a sudden, right, there's this novel combination, and
Yeah.
like there's a different affordance.
Yeah, affordance and intent also plays a role.
Exactly. It's just all of that is like it has to be accounted for somehow, right?
Yes,
So you have to
yeah.
detect that, and like does it like pull then like earlier stage recognition?
Yeah,
All of a sudden
that's
these things are like they touching and they've never touched in the training set.
right. That's true. Yeah. Yes.
That really, I'm curious more like about like the thought backing up,
Mhm.
human brain.
Oh, yeah.
Like, could that just be like, if I'm really close, the human could jump, and then I would have a lot more error. So if I backed up, like the human can't jump,
Right.
or something like.
Yeah. So the model is trying to predict the next frame, right? So here, that's sort of the what we've seen is that the prediction errors are more fine-grained if you do per frame prediction, and the prediction error does reduce if you take certain actions. And what we've seen is that it tries to keep the background as consistent as possible while making an action, and try to keep the errors only based on the person moving or anything completely new. So the first thing that we tried was to just put it in an open room. The model, like when we trained it in simulation, there was no chairs in that simulation, right? So the first thing it did in a crowded room was just keep going around circling the chair, right? Every single time we put it into any room, it sees a chair, it would just get attracted by the chair and just start to go and like try to take actions to circle around it. And it's just sort of building that even structure. And we just let it go for 10 minutes. And after a while, it just stopped predicting the chair and start to go looking at the window because it's never seen a window. So it's actively exploring by trying to minimize any sort of distractor variables. Sure. Oh.
Yeah.
Sure.
So, is it considering an error if it's like a random event? Like I'm imagining cooking and then you get a phone call.
Right.
There's no way to really predict that on previous frame.
Right.
Is that part of the penalty?
That's part of the penalty. So anything that the model cannot predict. So if it's not in its internal state of the current activity, it will tag it as a new event happening. Now, one problem here is that there could be multiple events happening, and the prediction error has to be fine-grained at the spatial temporal level. So for example, you get the phone call, right? But you're still stirring. So the activity never stopped. You get a different activity, right? So then there is the penalty does apply there, and it wouldn't probably be able to recognize that there were two events happening at the same time, but one started while the other was still in progress, right? But there is we're working on ways to improve this where you can have multiple actions and having errors at different granularities, and that's where the partonomy sort of flies in, because you can have two partonomies interacting with each other, right? So, it's more of a hierarchical thing, and it's really hard to get this simultaneous activities in an open world, try to handle at the same time. Right. Awesome. Right. Thank you so much for the opportunity.
There you go.
Right. Our next speaker today is Mark Lopez. He's a professor of computer science at ETH Zurich and the director of Microsoft Mixed Reality and AI Lab in Zurich, where he works with a team of scientists and engineers to develop advanced perception capabilities for HoloLens and mixed reality. He's best known for his work in 3D computer vision, having been the first to develop a software pipeline to automatically turn photographs into 3D models, but also works in robotics, graphics, and machine learning problems. Other noteworthy projects he worked on are real-time 3D scanning with mobile devices, a real-time pipeline for 3D reconstruction of cities from vehicle-mounted cameras, camera-based self-driving cars, and the first fully autonomous vision-based drone. Most recently, his academic research has focused on combining 3D reconstruction with semantic scene understanding. Please join me in welcoming Mark.
Okay, thank you. There you go. Okay, so if we look broadly at what my lab is working on, it's 3D spatial AI. And in particular, it's about understanding the world from sensors to assist people and robots to assist people to get stuff done and enable robots to interact with the world. These are some examples of. Sure. There we go. Yeah, and so essentially you see we're kind of building representations. Those contain geometry. semantic, and also affordances for the scene. Okay. So in terms of open scene or open world vision, for many of those tasks, it is quite important. And so I'll give an overview of some of the different works we've done in that space and kind of ongoing work. And so the first thing we really did in that space was essentially my student Sungyu Peng doing an internship at Google and doing open scene. So open scene was essentially a relatively simple extension of CLIP, which has essentially two encoders, a text and an image encoder that are jointly trained, so that essentially you generate embedding vectors that if the image corresponds to the text, you get embedding vectors that are mostly aligned. And so what we did was we froze that, then did through distillation, we trained a third network, what you see there as the red network, that also generates vectors, and those should be, this is essentially looking at 3D point clouds, but we trained from essentially data sets, the Matterport data sets, where essentially you have a lot of texture images aligned to 3D point clouds. And so there we could essentially train to generate aligned red vector embedding vectors for 3D point clouds that are aligned to the orange ones that we got from the texture images, and by transitivity should be aligned also to the blue vectors. Okay, what can you do with that? Well, so you would essentially, if you have a model like this one, you would pre-process it, compute all of the orange and red kind of ensembles of embedding vectors associated with all the points in the data set. And then when you enter a query, you generate a blue vector, you correlate a blue vector with all of the points in your scene, and you get the ones with the strongest response are probably the points of interest, right? So you see it here. It works for objects. It's fully open vocabulary. I inherit that from CLIP. And then, so you do, as you see here, objects, but you can actually also get affordances, materials, and all other kinds of properties that you might be interested in. So here we're still working with objects, but here you see, for example, as was mentioned earlier, affordances, and then we'll retrieve a number of those. Notice it even finds the bathroom, the toilet as a place to sit. Yeah, and so you see this here, right? Okay, so that was the first work there. This is actually kind of naive use of this on HoloLens at the time. We, of course, had to revive Clippy for this. This was also a pun for, of course, using Clip as our kind of image encoder. So anyway, so you can essentially hear, this is like a person wearing a HoloLens and then essentially saying what they're interested in. And then that translates and in real time gets essentially the points of interest. Here there was or speech recognition wasn't working properly. So for example, here the plants, and then it would highlight now all the points that corresponds to plants. And then, and if something would be out of view, of course, you could be navigated towards it also. Right. So here you see the coffee machine and so on. Then some further work we did. This was actually also in collaboration with Google, but in particular Francis Engelman, then a postdoc in my group, was driving this. It was extending the nerve representation to also encode that everywhere in space, also encode not only occupancy and color and so on, but actually also encode a semantic vector, a CLIP vector, essentially. Because of the high redundancy and this and that, you can actually do that quite compactly in an nerve setting, and then you can play around and do these kind of queries. Okay, then we switched to trying to look at instances. So we leveraged Mask 3D to detect essentially instances in a scene. Essentially agnostic of the semantics, and then based on for all of those detections, instead of doing it on a per point basis with some kind of unknown scale of kind of that it's actually using as a reference around the point, with objects we can actually use the scale of the object and find the best images with the right views of the object and no occlusions and this and that to essentially do the classification. It's also a lot more efficient because we don't have to do it now for all the points in the scene, but we can do it just for the instances. So here's a few examples. You can now do open vocabulary queries in the scene, as you see here, including some uncommon objects and so on. This essentially performed quite well. And also on closed vocabulary, it actually it's on par with the state of it was on par with the state of the art. This is roughly how it works. So you essentially do the open the mask 3D segmentation. So it works like this: mask 3D. You get instances. Those are class agnostic. And then essentially for each of the classes, you look for which are the images that are going to be best view this object. And so you select some of them. You also generate a crop now that has, both a tight crop and then a slightly larger crop that provides some context. And so we extract then embedding vectors for those. Here. Then we realized that although the previous method of mask 3D was open vocabulary, at the level of assigning a semantic label to the objects, the actual segmentation had been trained on a closed vocabulary, and in particular was always retrieving kind of a similar size objects, like chairs and things like that, but it couldn't really do parts of objects, it couldn't do other things. So that's where we then leveraged, wanted to also here try to, as we did before, try to go from 2D foundation models and lift those to 3D to be able to essentially do better. And so as we did before with CLIP, which is 2D, bring it to 3D. Here, we use SAM as a foundation model for segmentation, and then try to somehow lift that to 3D in our segment 3D. And so in particular, this was we did that by going over 2.5D segmentations, and so on. I won't explain too much in detail here. But anyways, this enabled to do these type of things where instead of being stuck with kind of always the same, roughly same size large objects, this segment 3D allowed us to actually pick small objects or parts of objects, as you see here. Then our most recent work in this space is actually going to be presented at the conference here. That's OVMAP. This is an open vocabulary instance semantic mapping. So think of doing the things that we did before, but now in an online mapping system. Okay. So that's what you see here. So essentially, on the one hand, we follow a little bit the same strategy as OpenMask 3D. So on the top part, we essentially are building a kind of a map as we go, and at the same time segmenting, class agnostic instances. And then on the bottom part, we essentially are selecting on the fly kind of the best images on which to perform the class assignment. Okay, and so this performs essentially on par with the offline methods as the one we had before, and also essentially is on par, outperforms typically the previous method that was also doing this, which is called OVMAPs, and so it's kind of performing quite well in that space. Okay, here's a few examples of instance highlights from arbitrary text queries that show kind of what then gets. And here's a system kind of in action, where you see it's kind of gradually starting to map the space and extend kind of the map representation and so on. And you see kind of what's been seen live, and then how the map is gradually built up, and different instances are generated and assigned kind of labels, et cetera, et cetera. Okay, so then a problem we also looked at that's closely related to this is just from single images, so not from 3D representation, but from a single image, be able to essentially do open vocabulary, kind of build on large language models, being able to recover not only 2D bounding box detections, but actually 3D bounding box detections. Okay. is so you see this is the kind of things that we're doing on a number of data sets. If you look at 2D open set object detection, you get these type of things where you can really ask. Let's see where my cursor is. Okay, so you can ask things like kind of specific questions, and then it will detect the particular instances of interest in the image. Okay, and so we wanted to bring the same to 3D. Which really starts by needing to lift it to 3D. We essentially use a monodepth estimator, which we then so essentially in this case we use unidepth. In the meanwhile, we would use this one. So this is our latest kind of work in the space. I forgot to add the year, but this is ICML'26. So it's an upcoming paper for monodepth, which gives really, really nice results. In particular, again, I'm trying to get the cursor here. So our method is the last column here. And compared to state-of-the-art monodepth methods, what you see is that it really does well on transparent objects. It manages to get those and also really gets the details. And how did we do that? It's essentially by not going to using a latent space diffusion model for the reconstruction, for the monocular depth reconstruction, but actually inspired by Kai-Min He and colleagues, going back to pixel space diffusion, which is what you need if you really want to get all the details back, right? And so that's where you see that we really get the bars of the chair and kind of also in the tree much more details. So anyway, so we haven't used this in the work that I'm talking about now, but this would be what we would use today if we revisit this. Okay, so here's kind of roughly the method. So we start from looking at an image and have an image backbone and a text backbone that allows us to then generate the typical 2D bounding box detections. But then we couple this with our 3D generation or depth prediction and couple it here and have essentially trained then the whole network end-to-end to generate the right. So it still generates depth here. The model. Trouble seeing my cursor there. So essentially we still generate depth, but at the same time we then also lift essentially our 2D bounding box detections here with a 3D head to essentially the 3D detection. And so this enables now open vocabulary bounding box detection. So based on so you can essentially now say, hey, I'm interested in this image in getting all of the chairs, for example, then it will generate bounding boxes around all the chairs. But you could also say, I don't care about the chairs, I just want the lamps. Then it will generate those and so on, right? So that's essentially what we have here. This is kind of showing that on open detection benchmarks, it's doing really well. Here's some more of that. There's also well in generalizing compared to the previous methods. And also on closed set, it actually is competitive with the state-of-the-art or outperforms many of the methods there. So here's a few qualitative results of that, where we essentially looked for here, for example, tables, lamps, and sofa, and then it would bring up detect those objects. Here, similarly, it finds the cars, etc. Of course, if you wanted to just detect everything that's in the image, you could start by essentially captioning and then feed the caption to this. Okay, a few more examples here. Okay, then another work we've been looking at. So as we look more at robotics and how robots could interact with scenes in a kind of open way, we typically use there one of the representation we really like to use is scene graphs. And so we would essentially, reconstruct this room, for example, and then we'd have chairs all over and some desks here and microphones. And then, for example, for the microphones, what we'd like to be able to figure out is, okay, for this microphone, which button should I turn here? So we want to essentially establish those relationships. So we can detect the buttons, we can detect the microphones, but then we don't know the relationships of which button is connected to what microphone and so on. And so this work is really about trying to explore that, potentially even have robots actually explore it. But the key is essentially to try to establish by leveraging LLMs and VLMs to try to leverage essentially all the knowledge that's embedded in there to at least get good priors essentially. So as you see here, we have a scene with a TV and there's on the table, there's a remote control, then we're essentially going to make a likely association. So it's a probabilistic graph, probabilistic scene graph, but we'll make a likely association between the remote control that's on the table there is probably the one that controls the TV. Okay, now if you have 2 TVs or you have 3 remote controls, then it's gonna, like somehow try to figure out what is what, and you could even have a robot potentially do some tests to clarify that. So this is roughly how the method is working. So we build up the graph using essentially kind of classical scene understanding. We populate our scene graph with all of the instances. And then at the bottom there, you see the functional scene graph creation, where we now make these functional connections between different elements in the scene. So for example, if you have in a kitchen, you have a table like a stove, and then you have different buttons, and you want to figure out which button controls which of the stove kind of elements, etc. So that's the kind of things we wanna capture. And so it turns out that compared to many of the more custom methods, by just leveraging the knowledge in foundation models, we actually relatively easily, was a bit of a surprise, we got essentially state-of-the-art results. Yeah, and by the way, this is also presented here at CVPR, this work. So here's some examples of the stove, where initially it might not know, again, my cursor there. Okay, so initially it might not know, so everything is kind of symmetric. It has some proximity. So it has some idea that, okay, probably this button is more likely to control this one, or maybe this one, and less likely this one, etc. So it has some a priori kind of estimates, but it kind of understands that these 4 things probably control those 4 things, right? And so it has this initial graph. And then when a person or a robot would do a test, you would actually then establish the connection and also update the rest of the graph. Okay, so then moving on. So we've also, and this is also actually a paper here at CVPR, where we're trying to go from validate the spatial reasoning gap that we see in multimodal large language models to a more open world setting, and in particular kind of outdoor worlds, and kind of essentially based on imagery that's captured by people walking around. Let me see. So essentially, specifically, what this is comparison to some other benchmarks, where the key is that this is really open world. It's people moving around, indoors, outdoors. The keys on the metric side, we really capture with proper stereo, LiDAR, IMU, and so on. We capture the actual correct metric measurements of the world, including also dynamics. So we're not only evaluating a static scene understanding of where the objects are statically with respect to each other, but also how they move about in the scene while you are recording and while you're observing the scene. So you see here, so in particular, the tier 3 there is this kind of dynamic scene elements. So the benchmark has all of those elements represented and has questions for all of those, and is evaluating then systems there. This is essentially our capturing pipeline that we developed here to generate all the data for the test, for the benchmark. And then this is a little bit how the different models are performing. So what you can see is we've evaluated some of the top models against human on a very small data set, because of course human patience is finite, so you can't have the human go through a gigantic data set. So that had to be limited. But you see, we're still very far from achieving human level performance on most of those tasks. But then if you look at the closed source models, do perform better than others on spatial tasks. But in most cases, but actually depending on the task, there's actually Quen, for example, can perform quite well on some of the tasks, in particular also the dynamic tasks. So it looks like models like Gemini and so on have been trained explicitly on getting some spatial understanding and those tasks. I mean, they've even publicly had blogs about this. So they do a quite reasonable job there. But actually on the tasks like dynamic tasks, they've probably not yet been trained on, and so there's still much more of a gap. Okay. Then I wanted to switch to the possible scene representations, and in particular, we've been doing work on essentially, instead of representing point clouds or Gaussian splats or kind of expensive representations, try to find very compact representations of scenes. And so this was presented last year at ICCV. Elisabetta Fedele, who is a PhD student in my group, was the main person driving this. Okay, and so the motivation was that traditional representations are essentially typically quite expensive. So points, triangles, and Gaussians, which are typically used now. So we'd want the models to be geometrically meaningful, compact, and modular. The goal is, can we move away from to better primitives? So obviously, Gaussian splats now are essentially ellipsoids, but you need many of them. And so what we explored here was adding a few parameters so that we can have a much more, much richer family of shapes that can much more compactly, be fitted to scenes. Okay, and so for that we use superquadrics. It's only 2 additional parameters, but you see that instead of just an ellipsoid, you can now generate, essentially represent many more scenes in shapes, and in particular shapes that might be very useful as primitives for kind of real world objects. Okay. Okay, so here you see, typical things are challenges with existing scenes. It's typically at the scene level. What we want to do was to more focus on doing this at the object level first. There's both optimization-based methods and learning-based methods. We'll go through that. So let's see. So essentially, the method that we propose starts from a point cloud. It has point features, 1 for each point. Then we have superquadric features, 1 for each superquadric. We have then a big transformer that takes all of this, and both essentially have self-attention between the superquadrics, but also cross-attends to the points. And then we get refined superquadric features. The initial instantiation of the superquadrics is just random initializations. And then essentially that also leads to a segmentation. So the cross-attention essentially gives you a segmentation, and the superquadrics essentially give you a much simplified shape of a very, very compact representation, with a goal that you could actually represent relatively large scenes for robots, for example, to manipulate by having very compact kind of representation, so that you can manipulate and interact, kind of have a robot with edge compute kind of interact with the world efficiently. Okay, so here's a few more things about the method. So of course, the more primitives you add, the better you're going to be able to fit the point cloud. But there's a trade-off there. So some of that. So this is showing here a little bit our method is actually selecting how many primitives are kind of needed. So there is a kind of sparsity kind of prior in there that tries to lower the number that are needed, kind of balances it out with the error. And then if we want to do a whole scene, we essentially start, and this goes back to the previous methods of first doing instance segmentation and then do the super deck on a per object basis. Oops, sorry. So this then looks like this. And then, so these are a few more examples. So here, then this is the decomposition. Notice, of course, the decomposition isn't perfect, but it's a pretty good approximation of the shape in general for most of the scene, and it's very, very compact compared to point clouds or any other representation. Okay, so you can actually also use this towards generative things. So here, for example, you can do a generative kind of images kind of steered by the representation. And then it means you can relatively easily edit this because you only have a few elements. So you don't have to move a whole point cloud. You can actually just move these few elements around, as you see here, then generate other images, etc. So that's just a possible application. Okay. Okay, so there's a few more. Okay, here we go. So then the latest thing we've been doing in this space is try to go a little bit further to make the shapes a little bit better even. So give them like few more degrees of freedom that make them even much better fit, be a better trade-off to represent many shapes. This is unpublished work at this point, but it essentially you can kind of already guess here what it's doing. We're essentially adding a bend to the superquadrics. Okay, so again, kind of same thing here. Oops. Okay. So we can very fast feed forward, generate essentially from, in this case, 4,000 points, go to 10 superquadrics with this additional twist or flex, kind of get to those type of representations. Okay. These are some of the other methods. And sorry for something went wrong between conversion from Keynote to PowerPoint. So there's essentially learning-based methods, optimization-based methods that essentially extract these kind of compact representations. So we're trying to actually get the benefit of both. So it has actually both elements in here. So here's a few more examples. And so you see we're extremely compact. So this is generated very fast. And it does a really good job at approximating it, because of this extra flexibility of bending things. So what we had quickly realized, and I don't know if I can still go there. There was one of the scenes here has long been a frustration. This one here, exactly. Okay. So you see the lamp here, right? The round lamp there. And so that one, because it's empty inside, it's really a struggle it was really a struggle to represent this with the superquadrics. There was always a big error there, and it just looked really unappealing. And that was the motivation to add this. That was one of the motivations to actually add this bending, this flexing of the shapes. Okay, sorry, I should have done this better. Okay, so this is then showing, and also there's something wrong with some of the conversion, but essentially you can see that compared to all these previous methods, our method essentially performs the best in terms of reconstruction, IOU, in terms of the compactness of the primitives, and in terms of runtimes, it's kind of on par with everything. And I'm sorry if things seem to have jittered a bit around. What we also did is to add additional robustness. So we trained also on point clouds that are not complete point clouds, because if you scan the world, you might scan the front side of the chair, but not necessarily the back side or things like this. Okay. And so we trained the method to this would be what would come out in a self-supervised way to fit this. But then if we do fully supervised, kind of robust variant here, we can actually have the method also actually complete the scene. How do we do that? Well, you can work from a partial scan, but you can actually, for the training data, you can actually also, of course, have a complete scan of the object and then just work from generating from partial scans, so single depth maps, for example, to from that still generate the complete object. If you have a scan of the object, you kind of know what you should generate. And so we can actually train our method to actually do this. Okay, so here's again some examples, the object point map that you have from the RGB image. You can do this for monodepth, for example, and then it would generate, and notice it generates a more complete scene. It adds a few elements that to complete the scene. It doesn't just reconstruct the front side, but it actually completes the object, okay? Which also allows it to remain more compact. As you, for example, see for the flower pot here, if you would only reconstruct the front side, you would actually need more primitives than if you complete it. So this actually is really very useful. Okay, so loss formulation, we have a surface loss. So we add these bending elements here, deformable superquadrics, and then we have the robustness where we actually learn to reconstruct complete objects. Okay, so here's a few more examples. But let me skip for that. Okay, and then the last thing I wanted to present is now really into the robotic space. And it's open frontier. It was just accepted at RSS this year. And essentially what we're doing here is, so we had done previous work on frontier-based navigation through networks that predict from the images where the frontiers are. So in robotics, one of the ways to do exploration is to actually detect the frontiers, which frontiers are there. So for example, here, if the door is a little bit open, then I see that there's a gap there, and then I see that there's free space behind there that I haven't yet kind of really observed. And so that would then be a frontier, right? And so here, for example, in the room, you can see that you have frontiers. Typically, you first train our model to efficiently explore a space and map out the whole space just based on the frontiers that it detects in images and predicts where they are in images without actually having a depth signal. But in this case, we've actually gone to a more open vocabulary kind of task-guided navigation. So the key idea is that I could just be exploring, but I could also actually be looking for a specific object. Okay, and so if I want to find a dining table, then I'm not just going to explore any random room. I'm going to try to find a dining room to then find a dining table in it. And that means that what the network does is it detects all of those frontiers. And then in an open vocabulary sense, we'll reweigh the frontiers based on, what's the most likely the frontiers that are most likely to bring me to my target, essentially, right? And so you see here different ones, and you see how, based on that, we'll actually pursue a different exploration route, depending on which task we actually do. And all of this is zero shot, right? So essentially, here's kind of the method in an overview of the method. From the image, we essentially determine a navigation goal. We have these frontiers based on, so the color code there tells you which frontiers we'd select. And here you see kind of how, for example, if you say, I want to find a chair nearby the monitor, it might be more efficient. It depends, like it might, or than just looking, here is the other examples. If you do plant versus plant in bathroom, the plant in bathroom is going to look for the bathroom, which it more easily finds, and then it finds the plant in the bathroom. If you just ask for a plant, it essentially isn't guided. So it's going to start exploring randomly all over the place until it finds a plant. And maybe the bathroom is not the most obvious place. So it might first explore other rooms for finding the plant, right? So that's really what this method is about. Here's some examples of this running in real, running. Let me see if I can move it forward. Something's wrong. I don't have the navigation bar there for the video, but I could let it run. But it essentially here it's continuously estimating new frontiers as it's navigating, and then it's essentially the task is to find a fire extinguisher, and then essentially we'll first I won't let it play here for sake of time, but essentially we'll first turn to the right to explore that frontier. It will realize there's nothing there of interest. Then it will essentially continue along the hallway. Eventually we'd find it all the way at the end of the hallway on the left side. It will find it. Now in this space, this is our robotic hall at ETH. For us also, it's not obvious where you should be looking for the fire extinguisher here, right? But and there are a few more examples here, which I'll skip through. Okay, so that was it. I think I'm roughly on time. So thank you.
Okay, I can put this right here. So the 3D perception work that you showed off was incredibly impressive. And I think one of the key challenges in 3D is that we lack data. We don't have nearly as much as the studio. So one of the I think selling points of these open vocabulary 3D detectors is you can prompt for any class. But I would claim that if you were to run this on ImageNet, things would sort of fall apart because things are very unconstrained in that sense. So what do you think, or what are your thoughts on, would you sort of agree with that statement, or maybe what do we need to do to get from where we are to maybe realizing this goal of running this on truly any image in the wild?
I mean, I'm not sure what you were saying when you mentioned it because that's actually not really in the wild, right? Typically, it's actually quite like has a class like in the middle of the image. It's kind of typically well framed and so on. So I'm not sure what you mean with that, but I certainly agree that in the wild, many of those things don't necessarily. There's many challenges to do those things in the wild. So I showed you 3D moods, for example. That works well on all the data sets where, like somewhat in distribution, where the data sets that we trained all of it on. What we realized is when we try to use this on a robot, like with a camera that's mounted on a robot that moves around the world and has different perspectives, typically, the results drop a lot. We've actually been doing some work on getting really good results there. The problem that we realized is that there wasn't any benchmark where we could show that our method worked. So there are really challenges there. I completely agree. So there's a big difference between solving benchmarks, which our community is kind of really prompted to do, and expected, like reviewers, we all expect of each other to kind of beat the benchmarks. There are clearly gaps in that because this doesn't always reflect really of real world performance and what we really would like as open world kind of real world performance. I think it's important for the community to realize where things don't work. This is actually really why also for myself, I've really pivoted towards doing much more in robotics because I really want to get things to work in the real world. Before I was doing it on a device like HoloLens with also the goal of actually having things work in the real world. So that's always been my interest, but it's challenging, and often it means you might have to do your own N+1 benchmark, but that tries to at least highlight some of the gaps. I really loved it when we would just put on the HoloLens and walk around and actually display the detection. So we would display the detections of kind of state-of-the-art models that supposedly outperform humans 90+%, blah blah blah. And then you walk around and it's complete nonsense. Half the stuff is wrong if you just feed it the egocentric images from your HoloLens, for example. So I think there's a lot to do in that space to get to true open world performance and things that are and essentially I think for this community really develop benchmarks that are really representative of that kind of those scenarios, real world deployments. But we've made a lot of progress anyways already, but yes.
Maybe kind of related, I'm curious how you found the generalization of the deep world model that maps from the point clouds to the super quadrants. Is that general and it kind of learns an objectness after training on Optiverse or something, or does it end up falling apart when you go outside?
Yeah, I mean, I haven't really kind of looked at that, so this would be a good question for Elisabetta. I think so. We haven't really explored it yet. So I'm like we've done some objects, but we haven't really looked at okay, here's objects that we know are not in Objaverse, and then kind of see how it behaves on that. So we've mostly focused on indoor kind of man-made kind of structures, which are well represented in Objaverse. So yeah, it's an open question.
In your opinion, would you say that the path toward generalization to the open world, the true open world, lies more in just growing our data sets to encompass everything, or is it more in the lifelong learning, active learning, self-attention stuff?
Well, I think there is some benefit in both. I think in addition, I think there might also be benefits in finding the right representations and finding the right inductive biases that correspond to, like the 3D-ness of the world and a number of other things. And, the physics and, gravity and a bunch of other things that would allow us to be more efficient, data efficient in many of those things so that we don't have to collect, infinite amounts of data. Yeah, so I think there's multiple paths to be explored there. Okay, anything else?
Thank you.
Does it work?
Um,
Hello,
could you do
hello?
me a favor and
Yeah.
turn on your camera, please?
Oh, turn on camera as well.
Yes, yes.
Okay. So I just have to turn on audio.
Yes, audio.
Okay.
So we'll see you there. We'll give it 2 minutes.
Okay.
For 10 more.
Sounds great.
Yes. Thank you. I'm excited to introduce our next speaker. Jiajun Wu is an assistant professor of computer science at Stanford University. Before joining Stanford, he was a visiting faculty researcher at Google Research, and he completed his PhD at MIT with Bill Friedman and Josh Tenenbaum. Jiajun's research group tackles the problem of physical scene understanding. By drawing inspiration directly from nature and human cognition, his work asks fundamental questions about the levels of abstraction AI systems actually need to make sense of their environments. His work spans multimodal perception across sight, sound, and touch, 4D visual generation, neurosymbolic visual reasoning, and embodied AI in robotics. Please join me in welcoming Jiajun.
Hey, yeah, thanks for having me. Well, that's a nice intro. I haven't heard that before. Sounds like maybe the AI has been improved a bit more. So, okay, but I'm going to talk about work that has nothing to do with frequency understanding. And also, this is also my first time giving this talk because I was like, open world vision, how is that connected to the things we've been doing? But it reminds me of some recent work that I've been doing, trying to more on the benchmarking evaluation side. So, okay, I'm going to talk about how we can benchmark these open world models, including a lot of these unpublished works that are just like, just being released. And to see that, I think everyone else is probably like, we have to come up with better open world models or navigation, data strategy. And I was like, how can we actually benchmark these models? Okay, so open world models, what does that mean? And actually, also I had a question about what is an open world model? So how is an open world model different from a world model? So I was like, okay, maybe I'll just, maybe we can start by looking into this popular term that people have been saying. It's like, oh, there's a world model. So world models can be then in many different ways, right? There's like video-based, Genie 3. There's like 3D, more 3D, like Marble from World Labs. There are also many different other types of world models that are somewhat maybe like learning predictive representations in latent spaces. So that doesn't even have visualized the component. But let's say we first restrict ourselves to the representations that are still visual. So you can actually see the pixels coming out. So in this case, what are the possible ways that we can evaluate these world models? Right. So, but to even before that, right? So before we can evaluate a video model, so is it possible for us to evaluate an image model? Right. So you can generate a beautiful image, and how can you evaluate that? Right. So for a long time, people have been saying, okay, now what we should do is we just compute FID on the ImageNet. And I think there's a question for Mark at the end. I was like, okay, the role of ImageNet. I think Mark correctly pointed out the ImageNet is not open world. It's very small. It's large by the standard of 10 years ago. It's by the standard right now, it's very small. Objects are centered and stuff like that. So it's not even open world. So can we actually do better than just using ImageNet? Right. So I think the zoom looks very, very blurry though. So let me see. I guess there's nothing I can do. Okay, I'll just continue. So the first question is, can we at least do it better than ImageNet if we want to evaluate image generation models before even worry about video generation models or 3D generation models, right? So our house. So this is our effort behind this work that is actually just released maybe a couple of days ago. So it's very fresh, called GPIC, which is a giant permissive image corpus for visual generation, for evaluating visual generation models, right? In particular, image generation models. That was led by Kashik, who is Feifei's student, and with Juan Carlos, and Kyle, who was co-advised by me and Feifei. So, I think the issues with current models for evaluating image generation models, right, is, they're either very small or they're unstable or they're non-permissive or they have both of these problems, right? So for example, ImageNet is kind of small right now, and then they're not very stable because you can only have URL. Actually, it's kind of stable, but it's not, the license situation of ImageNet is very unclear, right? And then there are larger data sets like Lion, but then, for a lot of these larger data sets, you can only download them by looking at the URLs, and everyone try to crawl URLs, and they just get a different copy of the data sets because the URLs some of them may become invalid, and also they're either small, they're unstable, or they have license issues. So we want to address all these issues, right? So that's why saying what properties should this new data set have? First we don't want it to be small, so we actually want it to make large in the sense that go from 1 million to 100 million images, and we want it to be stable so that we can host the raw data in sharded tar files so that everyone can download it. Right? So you download it, I could download it, we got the same copy. And then we want it to be permissive. So every image should have licenses that are okay for research and commercial use. So everyone, companies, industries, or schools can all use them. Right? So we want to have a data set of all these features. And that is the motivation behind GPIC. So first, why couldn't data set be small? Right? So ImageNet was considered large, but now compared with GPIC, it is very small. It's basically like 1 to 2% of GPIC. And because if the data set is very small, then if you use it to evaluate image generation models, like then what you can do is first there are two issues. Right? First is you can see that the number of token repeats is really crazy because the data is so small. When you train these models, right, you have to train like 1,000 networks on these small data set, and so it's really like it's overfitting to these large data sets, and also leads to I would say advantages, unfair advantages, disadvantages for different types of models. Right, so you have to really use the data a lot, and then so it's sort of overfitting. But also, if you look at the performance, there are actually studies that people are actually looking into. It's like, okay, how are you compare with diffusion models with autoregressive models when you train on large data sets once versus when you train on small data sets many, many times, right? So it actually turns out that there's studies from NLP and saying like, okay, so if you increase the data size sizes, then autoregressive models becomes actually more powerful because they're better at fitting these larger data. But if the data set is fixed, but then you have a lot more compute so that you keep training on these data sets, then diffusion models are much more constrained so that they can actually learn better overfit to the small data sets. So that's why you can see now ImageNet, these diffusion models, which I think is the top, right? So you can see that, actually, this is not exactly ImageNet, but this is like I would say a comparable experiment. So you can see that these diffusion models are showing red. They're actually performing a lot better, right? Having a much lower losses when you train on a small data set for 190 epochs. But the autoregressive models actually perform better when you train a much larger data set, same compute budget, much larger data sets with 1 epoch, right? So this leads to kind of very unfair advantage for diffusion models, and that's also when you use ImageNet for benchmark image generation models, right? It's just not very fair. So that's why we have to have larger data sets. Then we don't have these unfair advantages for one particular type of models. And second, one data set to be stable, as I said, because if you only have URLs of images and URLs, people take images up and down. So researcher one get a data set, which is only a subset of original data set. Researcher two get a different subset, and then they compute FID. They're like, hey, well, my FID is 2.1 versus your FID is 1.8. It's not really comparable, right? So because I just have two different sets of data. So I definitely want to address this problem. We want to address this problem. Before people cannot address this problem, a lot of times it's because license issues, right? Because this license is unclear. So if I just post a URL, maybe I'm okay. No, they're not going to sue me. But so if you can make sure that all your licenses are publicly hostable, you can download them and you can actually release the raw files, right? So And finally, you have to be okay with the license because I think we all, at universities, we probably don't care as much. We should care more. But industries, I think also different companies, actually, it's like every time you actually have a different lawyer, this is slightly different things, right? So you can, okay, I can use this license. We cannot use CC by SA. And another lawyer says, no, I can train on any license, but I just cannot say, I just cannot tell you. Or I can train on it, I can report, but I cannot release my model, right? So it's kind of all weird. So what if we actually have the right license for all this data? Right, so that's the motivation. The three motivations behind we having this GPIC, which is allowing permissive image corpus for image generation, visual generation. So you have 100 million images, and they're all permissible. CCBY is 80%, and they have public domain data, CC0 data, stuff like that. And we try to put together captions and tags. So use Quen, which is just open source vision language models. And you have tag, the different types of annotations, including tagging, short descriptions, long descriptions, medium descriptions. And it's centrally hosted on Hugging Face. It's MIT license. Everyone can download and use it. 100. And then we have train test bit. So the training has 100 million training images, and testing is 1 million. You have 200K for validation. But you also don't have to use a full data set. If you use the smaller versions, we have Light, which is 10 million image text pairs, and Nano, which is 1 million text image pairs. Okay. Okay, I think I'm going a bit too slowly. I'll move faster. But it's a new thing, which is great. So I want to advertise it a bit more. So the construction process, you have a source data, most of them from Flickr and some of Wikimedia. And then we do image filtering, and then we do duplication. And finally, we do caption generations. We just use this open source model Quen to generate captions in 4 different forms. And here are some examples. This is like a typical picture with a medium length descriptions, which is like motocross drivers in full gear rides, blah, blah, blah. And one more examples. This is a short description, like a gray fighter jet with LN or something. This is shorter descriptions. This is an example of a long description of the image. So you can see very detailed explanations of what's there in the picture. And another examples of the animals or more. And taggings. Sometimes we don't have tags, so we have to also using Quen to generate it, the blue car, yellow car, stuff like that. Okay, so and we did a little bit of comparisons about which Quen model to use as a 2B, 4B, whatever. So because we have to process 100 million images, so we try to achieve the balance between the counting annotation qualities in terms of how good they're doing counting, spatial relations, and stuff like that. So we have a small data set for benchmarking the captioning quality. And then we make sure that we pick the model that is having basically the best caption quality, maybe slightly worse than the 30 billion models, but is much faster, so that we can afford to use it to caption 100 million images. And then we actually train the baseline models on it. We just use just image transformers, train a 1 billion model using pixel space flow matching, train on one epoch because it's now larger. You just have one epoch on this entire data set, and then we get some scores. So it allows you to serve as a baseline. You can compete with them, right? Yeah. So yeah, and also we instead of using FID, we also there's a little bit explanations which you can see in the paper that we switched to FD Dino V2, which is less saturated, and then it's actually every of these learned metrics have their own problems. But FID is really just too old, and then so FID Dino V2, you can see that it's much less saturated. There's still room for improvement. I think there are papers on FID that you can see that it's like, it's already better than the test set or something, right? So it's overfitting to the extent it's actually much better than what you can get out of a test set, the FID. And then with more efficiency, I think 2 weeks ago, there's a paper saying you can actually optimize against, right? And they get even lower FIDs. So you can use FD Nano V2, and then which also correlates better than humans. And then we compute reference statistics on the GPIC test set, which itself is 1 million images, which is the same as the size of the entire image net, just the test set. Okay, so that's evaluating image generation models. Then we want to move on and say, okay, now we want to go beyond to say open world evaluation image generation models, but then what about open world evaluation of different types of world models? Right. So as I said, there has been different types of world models. Some are vision-based, some are 3D based. So is it possible for us to unify them into the same set of evaluations? So that's one attempt we did last year, where we tried to evaluate models that can generate things in 3D or 4D or videos in one single unified framework. So compare with existing benchmarks that are generating image or videos, they're like either working on very small scenes and they only serve like say video models, and they cannot really evaluate models like the output 3D or Gaussians as output. So how can we have, and also they often do not look at the spatial relations, because they focus a lot on semantics, right? So how can we do better in also understanding not only the semantics, like what, but also the spatial relations, like where, right? So yeah, you really want to understand if you have a word model that you can generate either it's a video or 3D scenes, whether it's capturing spatial relationships correctly, right? We address this problem by designing a unified work specifications that allows you to evaluate all these models in the share framework, right? So we design it in the form of you have current scene, and then you have some language descriptions. You have a camera motion as well. You have a camera motion that got specified either in the form of camera trajectories or in the form of language descriptions. So which tries to capture both the spatial prompts and the semantic prompts. What should be there semantically and what should be there spatially. And then spatial prompts can be like moving left, pushing in, all these different types of motions. And then we also try to separate camera motions so from scene motions because there are two different things, right? So sometimes we see a dynamic scene, sometimes it's a camera's moving a lot. But in those cases, you want to make sure that the scene is 3D consistent. But sometimes there's a camera's not moving and the scene itself is moving, and which is also very useful because sometimes you want to have a word model that is really capturing dynamics in the sense that you actually have scenes that actually move. So how can you disentangle them? Right, so we have our specifications about, sometimes we just move the camera, or sometimes we only want objects to move, the octopus is moving, right? So you can change the prompts and have controlled generation examples or testing cases to measure whether the system is actually following the prompts to either generate camera motions or scene motions. And then we look into different scenes. You have different types of indoor and outdoor scenes, different types of motions, including fluids, deformed objects, articulated objects, and stuff like that. And we use language models to generate semantic prompts. So this put together is our benchmark, which we call world score, which we try to give a score, for all these different types of world models. And the scores are divided into three different categories. The first is controllability, right? If how much I can control the camera, just like moving left, are you really moving left? And how much I can control the object, and how much is aligned visually and semantically with the language prompts. You have the quality, which includes the 3D consistencies. If you have moved the camera, the objects, getting distorted. Photometric consistencies, style consistencies, as well as the dynamics, which includes the motion magnitude and smoothness and stuff like that. All right, so then you can, based on all these metrics, you can compute two scores. One is the static scores. If sometimes you want to evaluate models that only generate, let's say, 3D scenes, so everything is static. So what if everything is static? You can compute a score only for the static scenes. But if you do model dynamic scenes, you can also have a separate score that captures everything as well as dynamic scenes. So we evaluated 19 models. That was the at this moment, it's like close to a year ago. So the models are, I think we have a leaderboard that we keep updating, but we're not very actively updating. So we're updating, so we're trying to incorporate once in a while the more recent models. But we do show that the system can be used to evaluate different types of word models, including video models, 3D models, or 4D models. So that was by Howie, who is an incoming PhD student, I think at Princeton, and Colin, who is my PhD student. Okay, so some findings back then when we did it almost a year ago is in 2025, we say, okay, the 3D models, they actually are still pretty good at getting 3D consistencies of the word models. So, when you move the camera, they're actually much more controllable in terms of camera motions. But, things could have changed, right? So now, if we look at, actually I have, there's a new release of VO4 and we don't have a chance to test that. But I think it'll be great to test, how well they are doing now in terms of these camera controllability. Yeah. And also back then, these video models are not as good in generating very, very large worlds, right? Because you can keep expanding things like that. But things could change too. So it'll be nice to also explore, how these models have evolved in dealing with all these situations. Okay. So up to this moment, when we talk about evaluation of models, they're like image generation models, 3D generation models, video generation models, 4D generation models, but it's all passive, right? So things may generate, they may move themselves, but there's no active exploration. Just do everything in one shot. You have some model that have generated something, which can be images, videos, or 3D. You want to evaluate it, right? But if you really have an open world situation, then your model may have some ability to interact with the real world. You say, I want to go forward, go backward. So how can you evaluate that kind of models, right? So want to go beyond also from passive to active explorations. So, instead of just generating, you have a model that can understand, let's say a sequence of images or videos, right? But what if the model is actually outputting, some actions? Now, in this case, let's first look into this action, which is going for, let's say the action is just like moving cameras, right? So if the model can output a moving camera, so is that possible for us to also benchmark and compare these active exploration models compared with models that only do passive observations? So that is the motivation behind this recent effort that we also, I think, just released. It's still just finished and submitted, called ESI Embodied Spatial Intelligence benchmark. So it's a benchmark where agents can move, look around, and manipulate to acquire evidence for better spatial reasoning. Right. So now there's really a perception action loop. You observe something, the model can produce action, and the scene is going to respond to it, and then you can iterate on how these models are solving problems. So we designed 10 different task categories, including 29 subcategories and over 3,000 instances. The 10 categories can be roughly divided into 4 major categories, including object representations, like what about perceptual grounding, physical dynamics, about number representations, including counting, layout, geometry understanding, as well as the goal-directed actions like agent behaviors. And then we have 29 subcategories. Within each categories, you have a few different types of tasks. The reason about I have to. Unfortunate news. I think PowerPoint is frozen. So maybe I have to quit. Yeah, I think it's PowerPoint is dead. But let me finish this slide, and I have to force to quit. So you have 29 subcategories. You can see that we asked questions like, let's say, physical structures about liquid volume and deformability, and column mapping. It's about like traversability and navigation and all these kind of things. Okay, let's see what to do. Force quit. Okay, great. Okay, I'll move to the next slide, just in case it goes again. Okay, great. So some examples about when you're reading about physical structures, you ask about liquid volumes, what's under the cloth, and rigid containment and stuff like that. And for specular reflections, you ask about reflection entry, is it planned in the mirror or is it real? And spatial relations and all these different things. For physical dynamics, you're like, oh, can the apple rest on the slope? How to stack and stabilize different types of objects? And spatial relationships, including are there 3 objects in a line? Do they form an equilateral triangle? Are they touching each other? And we can do counting and stuff like that. And temporal understanding is like, oh, how many trees has the object passed? Are there any change in the box? And you can do different types of questions. And let me give you one example about how this benchmark can support the reasoning or evaluation of active open world exploration models. Right. So here in this case, you're only given the last frame of the videos. So, right. So, here you're given a frame like this, right? So it's like, okay, now what object is under the class? So you're given us a frame like this, and then you're like, okay, if you directly ask the VLM, the VLM may say, okay, according to the shape, it looks like there's a cup, right? So if you only do that, that's just like, you're not doing actually enough exploration, so the answer may be not correct. But if the model is able to actually reason, okay, say maybe I have some action space that you can be pre-specified, and it would be like, oh, change to another view, then you can actually get a different view observations. And then, or alternatively, you can say, oh, maybe I would just do grasp the class, right? You can take different action spaces and give you more information. And you can see that, with these different actions that are being taken, and after that, you have additional observations, which you can see that this helps the VLM to answer your questions more correctly. And it's probably not surprising that, doing some initial evaluation, this is a benchmark, so we're not trying to propose a new method. But just like if you took a few existing methods, you see that the methods that allows supports active exploration is actually doing a lot better in reasoning, especially about occluded scenes and stuff like that. And it also turns out that if you just have multi-view, you just have, instead of giving the model a single view input, but now you give a multi-view input, it's actually not really directly helping, right? Sometimes you really have to do active exploration, including like move object way, to better answer questions like connectivity and stuff like that. And also, still, there's like a big gap between the humans' performance and the model performance. Like humans are still much better than even the best, the vision language models, including like Gemini or GPT-5 and stuff like that. But there's still some work that we can do in this space. Right. So that was led by Ini, who is actually a postdoc with Yejin Choi from our department. Okay. So finally, let me talk a little bit into robotics that we want to explore how we can do benchmarking in the real world environment, not real world, ideally real world, open world environment that we can do actual robotic evaluations, not just actual perceptions, but then benchmarking how we can have solutions of, let's say you have a robotic system that have policies, right? Not just like going to the left or open something, but really have a robotic system that have the policies. Then how are these dealing with solving robotic problems? So in this effort called bench behavior, which we have been working on for many years now, so we designed systems that we first ask humans, what do you want the robot to help you with? So instead of coming up with tasks ourselves, we asked him, we did a survey, and do you want the robot to help you cook breakfast or clean the bathroom? And so we look into activities that people do in daily life, run the survey, and turn out we get a ranked list. And the first one is you want to clean a house, robot to help you clean the house after a wild party, right, which is most needed. After that is clean the shower. And after that, something like a set a dinner table or cooking dinner is somewhere in the middle because some people like to cook things themselves. So we have these kind of a ranked list of activities, and then we pick the top 1,000 activities that people really want robot to help you with. And then we want to set up evaluation benchmark to evaluate, in some sense, it's more or less it's open world to the extent that you really deal with all the activities that deal with in your real life. And then for each of these activities, we actually design domain description language that specifies, let's say, if I'm a robot to help me pack lunch, what does it mean by a successful activity? Right? So you have to define the initial conditions and the final conditions about packing lunches. So maybe in this case of a packing lunch, there's a water bottle is on top of the counter, apple is in the fridge or something. But as a final condition, you have a pair of a box, and then for every so for every box, there's a hamburger in it, there's a water bottle in it, there's an apple in it, right? So this is like your lunch boxes for CVPR. So this is like final conditions. So you define these initial and final conditions for each of these activities, which allows you to actually benchmark whether your robotic solution is solving these problems by satisfying these predicates. And then we also support simulations that you have to collect. It just really requires a lot of effort to build and collect these diverse scenes and objects that supports these kind of simulations. And then we do a lot of annotations to make sure that everything is plausible, consistent with our description language and stuff like that. With the hope of eventually, we'll be able to actually benchmark and generalize from training simulation, which you can see on the left, to eventually transfer to real world. So we actually have a real room in our basement of the Gates building that try to be aligned with the simulation, so that with the hope that we can also test a little bit into the transfer as well. So that was that by Rohan, who is postdoc with me in Feifei, and is going to be assistant professor in Northwestern, and Eric, who used to be a PhD student at Stanford and now at OpenAI in Feifei as well. Okay, we actually also ran a challenge. So last year at New Rips, we actually ran a first challenge with participants from NVIDIA and many other, industry and academic labs. So we picked, to do evaluation with 1,000 activities is too heavy. And we also don't have really the higher quality annotations ready because we want to also provide not only the states, initial and final conditions, but also some demonstrations, because otherwise the problem is very difficult. It's really long horizon. So we want to collect some demonstrations so that people can serve as a basis for things like imitation learning. So we picked 50 tasks, and then we collected demos totaling 3,000 hours, even just for these 50 tasks. And then we provided some baselines so that people can try to compete. So I think it was a great success. And this year we're going to have it again, but probably at Coral, for the behavior challenge. And building on top of behavior, we have designed a few other smaller benchmarks that can try to calibrate, understand models in different ways. So one of them, which I will talk about as the last piece of the talk, is we can use this behavior environment where we now already have the annotations of objects and scenes in form like scene graph, as well as the predicates conditions, whether objects is on the table or not on the table. Then this can actually allow us to very easily evaluate how these vision language models are doing in embodied reasoning, not just like answer questions. Before I said I have this benchmark which about answering questions. You can move to the left, you can pick up the piece of cloth, and you answer the question about what is under the cloth. But here, the goal is not to just answer questions. The question is really about understanding the scene dynamics and make predictions. So in this work, which is led by Manling, back then was my postdoc and now assistant professor in Northwestern, and her student, Qinan. So what we did is, we leverage behavior, which gives you object states and robots, right? And then you have a state spaces, you have observation space which you have the action spaces that are all kind of already provided by behavior. But then you want to reason, to what extent can vision language models or any type of models you want to use can do it in word modeling. In word modeling, in the sense that how much can you do forward predictions and how much can you do inverse predictions? So you can think about it as you have a POM-DP, partially observed MDP framework, right? You have current observations, and maybe you construct some scene representations out of it. You can apply some actions, and then of course the scene state representation is going to change, and then objects going to be moved to different places, or the scene representation is going to change. You'll get updated observations. You get these kind of POM-DP formulations, but then your goal is, so to reason about, given this simulated manipulation data sets where the robot is actually doing different things in behavior, right? So at the very beginning, maybe the robot is holding this drill. And you extract keyframes and the scene graph representations, as well as the changes that all the actions lead to. So in this case, maybe at the very beginning, the drill is on the table. After you grasp the drill is no longer on the table, right? Now this is a state change, a predicate change. And the robot is moving the drill to different locations and also at the same time grasp a screwdriver. So now you have this additional updates. That is, the scene graph or the state representation has changed once more in the sense that now the predicate of grasping a driver or screwdriver is being grasped is being satisfied. Right, so you can see that all the states, because it is a simulation environment, which is very nice because you can have all these actions that lead to what exactly state changes has been provided. And you have perfect ground truth that allows you to benchmark and test whether VLMs can make these predictions correctly, right? So I'm going to skip some of these. These are long demonstration sequences which we have collected, and you get all these state changes over time. So now you can set up problems, right? The problems that you want to benchmark, you want these models to solve is first forward modeling, which is like, okay, if I tell you what my actions are, right? If I go from the current state, this is my original state, and I'm going to apply different actions, and the state is going to change, and the observations are going to also change. But then if I reshuffle all the frames, I'm like, okay, now, you're going to get multiple observations at this kind of random order, right? Are you able to, if you really understand the state transitions and what actions are leading to what changes in the world, then can you actually reshuffle these randomized frames so that I can reorder them to matches the correct order, right? So this is a forward modeling problems that ask reasonable predictability of these vision language models or any types of models you want to benchmark. Right. So the goal is, whether these models can actually reshuffle these frames so that they align with the actions or state changes have been happening. At the very beginning, I move the drill, lift it from the table. And then second, I grasp the driver. Third, I move the screwdriver also up to the make it leave the table. And finally, I put the drill inside the toolbox. And then similarly, we can also do inverse modeling in the sense that, you're given all these observations. So you're like, okay, this is my current state. I have all these future observations, but I know that, there's a collection of actions that has been taken, but I'm provided with these actions in a randomized order, right? So actions have been randomized. And now the question is that possible for me to go from these randomized, having shuffled actions to reorder them so that it aligns with my visual observations? Right? At the very beginning, I didn't execute the action of put a drill inside the toolbox. Right? The first action I took is actually just to grasp the screwdriver or grasp the screwdriver. Right? So you can reorder or grasp the drill. So you can reorder all these actions. So whether the model can reorder all these actions actually is a reflection of its inverse reasoning capabilities, because now you have to infer the actions from these randomized, from these state sequences, but then you have to reorder these actions from the randomized orders. So, as one example, right, you can build behavior, you can do a lot of different things. And this is one example. We use it to do forward and inverse modeling capabilities, test the inverse and forward modeling capabilities of multimodal language models, vision language models. You can see that these models, their performance are pretty good if the steps are pretty short, like 3 steps, but then there's a sharp degradation when you reason about long horizon manipulation problems, right? They're not as able to correctly reorder the tasks or the actions or the frames. Well, in comparison, human performance is always pretty high, right? So there's a performance decrease when the problem gets more complicated, a longer horizon. And they have a slightly better performance on inverse settings about reordering actions compared to reordering frames. But there's a big gap between human performance and model performance. So there's still a lot to do. then sometimes I would say, the open world evaluation of the world models is just really at the very beginning. We talk about a few things, evaluating image models, evaluating language, video models, 3D models, and we talk about, spatial reasoning, and doing a little bit of actual perceptions. And finally, building a benchmark that allows you to not only do actual perceptions, really testing manipulations and reason about scene dynamics. I think there's really has been exciting progress, but there's still really a lot to do. And this problem is very difficult. Yeah, thank you.
For the first data set,
GPIC, yeah.
yeah, for GPIC, what was the approach towards managing or detecting any instance of hallucination for the generation of the captions?
Oh, so
You have 100 million image text pairs, a lot of them generate by Twitter.
yeah, so we have a smaller set. I think we picked like 2,000 pictures, and then we actually tested when, on 2B, 4B, 30B, AB on the captioning results. And then we actually have, manual, just like human, just to check these captions, and then compute accuracies in different fronts, whether it's accurate in terms of counting the numbers, spatial relationships, and stuff like that. And then, unfortunately, no models are going to be perfect. But you can see that our bench, after testing, we realized that, okay, these models are having a pretty high scores in terms of consistencies. And then we picked the ones that there's like 2B version, 4B version, 2B is the fastest, but has a slightly lower accuracies compared with 4B versions, stuff like that. So, and also OCR accuracies. So we picked models that give you more or less the highest accuracies, which also give you high throughput because you have to use it to capture 100 million images. But because it's automatic, so I think we try to pick the models that can provide accurate captions to the extent we can, but I think, I'm sure there will be errors. Yeah. Thank you. Great, thank you.
Yes.
All right. We've had a wonderful half-day workshop with very interesting and engaging talks. So we're going to wrap up this workshop with a challenge. A short introduction on myself. My name is Nihar Perry. I'm an incoming postdoc at Caltech, and a lot of my PhD research was in learning from few shot demonstrations. So in that spirit, over the past few years, we've been running this challenge called the Foundational Few Shot Object Detection Challenge. Why is there a green line? Maybe stop share. Share again. Okay, now we're good to go. All right, so this is the sort of third iteration of this challenge. And this challenge was really motivated by the sort of remarkable progress that we're seeing with these zero-shot open vocabulary detection models. So broadly speaking, these models, given some text inputs, you can prompt them and they will detect everything in your scene. So the natural next question is, if these models are so good, can we actually use them as automatic annotators? And it turns out the answer is not quite. And there's a very clear distinction on why this is the case.
So if you ask a model, if you deploy it in this environment where we ask it to sort some debris, I can prompt a model for a water bottle, and there's a pretty good chance it'll do something reasonable. But if I prompt it for something like high density polyethylene, there is a very, very good chance it has no idea what it's supposed to recognize. For the basketball fans in the audience, if I ask the model to detect a person, there's a great chance that you'll get reasonable responses. But if I specifically want it to find Jalen Brunson and identify the number on his jersey, there's a pretty good chance it's not going to fail if I just ask in one prompt. So this sort of raises the natural question of how do we actually deal with this gap between what these VLMs can do and what we actually might want them to do in practice. So maybe another trivial example here, which Shu motivated this workshop with here, is that VLMs seem to struggle with distinguishing trucks and like the definition of a truck and a bicycle. So this is an example from a data set called new images. And according to the new image annotator instructions, a truck, which is sort of the ground truth is shown with the red box here, a truck is only the cab. But if you ask any off-the-shelf VLM, it'll draw a box around both the truck and the trailer. And it's not that the model's prediction is wrong, it's simply misaligned. So the VLMs inherit the biases of their training data set, and there's this gap between what these models learn from internet scale data and how we actually want to deploy them for our practical purposes. So again, this is the sort of gap that we want to address. So we can also take inspiration from how we as humans have tackled this problem. So if I were to ask any of you guys to label a truck, maybe some of you might also make the same mistake of only labeling the truck cab instead of both the truck cab and trailer. So the way we get around this is when we talk to each other, we give each other visual examples, we give each other rich textual descriptions, and more often than not, we actually give each other negative examples of what not to annotate. So we can actually align our foundation models to think like like we do as human annotators. We can do this by fine-tuning these foundation models with a few shot multimodal examples. So this is the motivation and setup for this challenge. And for those of you familiar with the few-shot object detection literature, this problem setup of providing a few examples, this is kind of exactly like the few-shot object detection challenge. But in this world of foundation models, foundational VLMs, they violate the current benchmarking protocols. So importantly, according to the standard benchmarking protocols, we need to have a very clean split between what we call base classes and novel classes. So base classes are things that you've seen during your training, and novel classes are things that are fully disjoint. But if we think about these foundation models like CLIP and Gemini, we have absolutely no idea what they're trained on. So there's no way or no guarantee that these models obey this split. And this also sort of naturally leads to this idea of concept leakage. So because these models have been trained on such diverse classes, that there's no way of ensuring that the new class that you're showing is truly novel. But I would even argue that maybe this doesn't actually matter for practical purposes of how we want to use these models for real-world applications. So another neat insight here is that zero-shot VLMs beat out state-of-the-art few-shot object detectors. So everything above is kind of a purpose-built few-shot object detection setup. And what we've done here is we've taken a state-of-the-art open vocabulary detector called Grounding Dyno, and without any fine-tuning, we just run it zero-shot, and it's able to dramatically outperform everything else. So this clearly tells us that if we use these foundation models, we can make a lot more progress towards solving these sort of real-world problems. So we shouldn't artificially handcuff ourselves or put our hands behind our backs with this artificial split of base versus novel. So the claim here is that pre-training on large-scale data will be a key enabler for generalization in the open world. This sort of sets up this challenge. So foundational VLM should enter this conversation of a few-shot object detection. So rather than avoiding this notion of concept leakage or enforcing strict base and novel splits, what we really want to do is we want to say, okay, you can train your model on whatever you want on the internet scale data that you have, but for our particular test domain, you can only fine tune on a few examples. So we think this is a much more realistic protocol for how we want to use these models in the real world. Okay. So a lot of the examples I've been giving you thus far have been about driving data sets. But unfortunately, these driving data sets have many objects that are quite common on the internet. So things like buses, trucks, cars, and pedestrians. So if we really want to stress our models on outer distribution classes, we really need to collect and evaluate on truly out of distribution data. And to this extent, we collected a new data set called RoboFlow 100VL, which is a multi-domain benchmark for VLMs. And this benchmark has a number of weird and wacky categories like thermal imaging of power infrastructure, aerial images of sheep, and medical images of liver disease. And this data set, just to give you a broad overview, this is a collection of 100 unique domains. It's about half the size of Cocoa, so this is the perfect size for academics to get involved, but it has 7 times the number of categories. So these are a lot of really rare and fine-grained categories that you don't typically find in your internet scale pre-training. And that's what makes this data set so difficult. And a little bit more on why this data set is different. A lot of the categories, to give you a sense, we have context-dependent class names. So here on the left, we have a volleyball player. The class name which we use to describe this action is block. But mentally, if you think of block, maybe you think of a Lego block rather than this type of action. Similarly with Thunderbolt, maybe you might be thinking of lightning. But here, this is a type of soldering weld on some wire. We also have scientific acronyms and concepts. So for those of you that may have broken some bones in your hand, maybe you might be familiar with the MCP. But this MCP is very different from maybe what the LLM folks might think of when you say MCP. So there's very, very clearly a lot of language collisions there. We also have catch-all categories like paper and soft plastic. So obviously these are very poorly defined versus something like a car or a truck. And lastly, we have these multimodal imaging modalities, as I mentioned earlier. And importantly, for each of the data sets in this sort of benchmark, we provide multimodal annotated instructions. So for every class, we provide few-shot visual examples and some rich textual descriptions. So for example, here we have a soft plastic. And with the soft plastic, we have the description. Soft plastic is often transparent or semi-transparent, featuring flexible, wrinkled appearance. It may be found in the form of bags or sheets. So given the class name soft plastic, there's a good chance that you might not know what I'm referring to. But now that we have this rich textual information, I think it becomes much more clear. Okay, so now this sort of sets up the groundwork for our challenge. And in this challenge, this year's challenge in particular, we had 2 tracks. So we had an overall track where folks could train their models on whatever internet scale pre-training data, and they could fine tune on 10 examples per class. And instead of setting up this challenge on all 100 data sets, we looked at a much smaller, more manageable set of 20 data sets. And we had a second track called the in-context prompting track, where we really wanted to challenge people to think about what you can do without gradient-based fine-tuning. Because oftentimes this is quite expensive in practice. So without gradient-based fine-tuning, maybe you can construct better input prompts. Maybe you can come up with better augmentations or better post-processing strategies. So these are the things that we were sort of hoping to see from the community in this regard. Another quirk about this data set, or the few-shot object detection setup in particular, is that few-shot object benchmarks are federated data sets. And what this means is that each image in this data set is exhaustively annotated for a single category. So on the left, you see a bus. So this is technically a fully annotated bus data set, because every bus in the image is fully annotated, and there's only one bus. All right. Similarly, on the right, you see a motorcycle. There's only one motorcycle in that image. It's fully annotated, but we have no information about any of the other classes. And for evaluation metrics, we just use good old-fashioned mean average precision. So for folks in the object detection community, this is a very standard metric, which we all use. All right. Now, with respect to baselines, for our overall track, we simply took state-of-the-art detectors and fine-tuned them on our 10-shot examples. So we have models like RFDetter, which is not pre-trained on large-scale data sets. And we can fine-tune this on 10-shot images, and we get an average accuracy of about 32. And then we take more sort of recent foundational models like DEDIC or Grounding Dino. We can fine-tune these on the same 10 examples, and we can see that there's a huge delta between the zero-shot performance of these models and the sort of fine-tuned performance. Once we've aligned these foundation models to our target domain, we see a significant increase in performance. All right. And for our in-context prompting baselines, What we did was we took a suite of the latest foundation models like Qwen 2.5 VL, Qwen 3 VL, and Gemini 3 Pro, and we actually tried prompting them in two ways. So the first thing you can do is obviously you can just prompt with class names alone. And as I described previously, class names are sometimes insufficient. So if we actually augment our prompt with not only class names, but also with these rich textual instructions that come with our data sets, we see a pretty consistent improvement in performance between class names only and class names plus instructions. So these multimodal large language models are uniquely capable of in-context learning. And this is something that this baseline kind of highlighted. And to this end, we actually found that because these base set of instructions improved performance so much, one of the natural questions to ask is, rather than just using the set of instructions that we get with the data set, is there actually a better set of instructions which might be more well suited to the specifics of the model? So each of these models is trained on different data sets. They respond differently to different prompts. So we want to leverage this insight. And the way we do this is through prompt optimization. So prompt optimization, you can think of as an automated way of taking the prompt, taking some initial prompt and given some objective function, iteratively improving this prompt. So what we find is our approach is that we use the model, we allow the model to update its own prompts based on the predictions. And importantly, the way in which we guide the model to update its prompt is we want it to change its prompt to include the false negatives and exclude the false positives on the training set. So given a model, you can ask it to make zero-shot predictions. And once it's made these predictions, we can identify the set of objects and the ground truth from the training set that it missed. And we want to update the prompt to make sure it includes these examples. And if it has some false positives, we want to make sure we are more precise in our prompts to make sure we can get rid of these false positive examples. So maybe I'll ask the audience a question here. So given these two examples of serve and attack, they look quite similar on the surface, but I'm curious if anyone has a way in which you might want to differentiate these two items or two classes. That's a great point. So the key difference is how close they are. So the person that's serving is much further away from the service line, whereas the person that's attacking is playing at the net. So these are the sort of fine-grained details that the initial prompt might not capture, but we can actually, through prompt optimization, allow the model to discover this better prompt on its own. So this is sort of the high-level idea of this improved baseline. And as we see, we try this across a bunch of models, and our baseline here was the strong baseline that I showed before with class names plus instructions. But now, instead of using the standard instructions, if we use our optimized instructions, we see consistent improvements across the board. And the trend here is pretty clear that prompt optimization may one day outperform fine-tuning. So right now, if you fine-tune grounding dyno, it still does pretty well. But there's a clear trend. So Gemini 3 Pro is within a couple percentage points. So hopefully by Gemini 5 or Gemini 6, maybe there's hope yet. All right. So these are the baselines. And now we actually ran this challenge, and we had a great response from the community. So I'll talk about these two tracks separately. So first, for the overall track, we had submissions from 17 teams that made over 200 submissions. And the leading method from Superb AI beat the previous best method from last year by about 4%. So this is pretty impressive. And then above and beyond our strong baseline, I think all teams did remarkably better. So a couple of high-level takeaways here. Detectors perform best on industrial applications. So I think this really says something about the types of data that these models are trained on. So when we fine-tune on these data sets, we see a pretty big boost for industrial. But in contrast, for the medical and sports data sets, we see the detectors perform not nearly as well. So this is one of the benefits of having a benchmark with so many diverse categories, is that we can actually sort of evaluate our model's performance across very diverse categories. So let me sort of briefly talk about the two winners of this challenge. So first is Superb AI, and they come up with their own bespoke architecture, which is a multimodal promptable model, which is fine-tuned on large-scale in-domain data. So this model can be prompted with text or even long paragraphs. We can prompt it with boxes, points, or even a scribble. And then it takes the image input and passes this through a standard encoder. And given a large transformer, we can, you can think of this like a standard debtor-like pipeline. We can then, get better high quality results that can be adapted in domain. But above and beyond the strong base data set, this team basically proposes two things to improve the input and two things to post-process the output of this model. So first, they talk about discovering the unknown. So as I mentioned, a lot of the prompts that you get from the RoboFlow data set, they're not quite all that informative. So what you can do is actually use the model itself to come up with more informative aliases. So, given the soft plastic, instead of just defining it as soft plastic, given these image examples, maybe we come up with the aliases plastic bag, thin film, transparent sheet. And similarly, they also find that the few shot examples or the few shot images are quite restrictive in terms of the amount of data that you have to train on. So you can actually take the initial set, fine-tune your model, and then use this fine-tuned model to then pseudo-label the rest of your training set. And this expands the training set and improves performance. So the second part of their pipeline is, now that you have a really strong fine-tuned model, they want to identify different ways of post-processing the data. So the first thing is category-specific thresholding, and this is very common in the open world literature. So your model does not have the same sort of confidence calibration across these diverse classes, so we need to treat each of them differently. And then lastly, they reclassify the high confidence boxes for correct labels. So what I mean by that is they train a small MLP on image crops. And the purpose of this is to basically ensure that your model is not incorrectly assigning a high confidence to the wrong class. Because according to the MAP metric, this would be very bad for your model's performance. So those are the sort of key takeaways from that method. And then we have our second place winner from FDuro iLab with 51.6% performance. And their approach is quite straightforward. So they really lean into data augmentation. And their key insight is that we can leverage instance segmentation models to perform copy-paste augmentation. So here we have an example of one of the data sets. It's a bunch of apples on a tree. So we can segment out this apple, and we can apply different augmentations to this apple. And this is sort of your standard image augmentation toolkit. And given these augmented image crops, you can then go and paste it into the image to dramatically increase the size of your training set. So once you've done that, you can then fine-tune your model. And given this fine-tuned model, what they find is that oftentimes this fine-tuned model makes incorrect predictions. So here, given this image, the model initially predicts this as a turtle. But it turns out that these multimodal large language models are actually very good classifiers. So you can take this image crop and you can ask Quen, is this a turtle? And it will tell you, no, it's not a turtle, it's actually a penguin. And you can use this information to relabel your model's predictions. So importantly, they're making this distinction here of they want to use a standard object detector or a grounding dyno style specialist model for the initial set of predictions. And then they relegate these multimodal large language models for the task of reclassification and post-processing. All right, so that was the overall track. And next, I'll talk about the in-context prompting track. So we discussed our very strong baseline, which we call DETPO, which is through prompt optimization. And we were quite pleased that folks in the community were able to significantly outperform this baseline further still. So first, I'll talk about Lababa. Before I get into that, sort of some high-level trends here. So detectors tend to perform best on flora and fauna in this in-context prompting track. And it's important to note that because you can't actually use gradient-based fine-tuning, now we're really relying on the data distribution that these models have been trained on. So somewhat intuitively, it makes sense that probably there's a lot of flora and fauna on the internet, but these models do quite well. And maybe unsurprisingly, there's not that much medical data on the internet. So, the detectors, they perform worst on medical images and sports images. Okay, so now getting into the key insights from Lababa. So their method is kind of an ensemble of many different fine-tuned methods. So given some image inputs and we have these rich textual descriptions, they take they basically construct a very strong prompt. So they consider the data set specific class definitions, the visual examples of the few-shot training set, negative instructions that might confuse the background, and given this input, they prompt three different types of models. So they prompt Quen, they prompt a model called Duobao, and SAM3. And given this this big set of predictions, now they can post-process these using your standard NMS strategies and confidence calibration, a lot of the standard techniques which one might expect to use when you're ensembling predictions from a lot of methods. And they find that this strategy works quite well. And second, we'd like to highlight MR-UCAS, which takes a very, I think, interesting approach here, where given the input images, they actually have a two-path model. So for the for some set of images which are sort of easy to detect, they use a multimodal understanding model, something like Quen, to directly extract bounding boxes. But for classes and data sets which are not so easy to detect, they actually use a multimodal generative model. And what they do is, given the image, they simply ask the generative model to draw bounding boxes on this image. And I thought that was a really cool technique here. And you can use standard image processing techniques like thresholding based on color, just to find the bounding boxes that are drawn by the image model. So now, again, this is an ensembling-like technique. So given this two-path model, you can take your predictions from both sets, and you can perform your NMS, you can perform scoring recalibration, and this gives you your final set of predictions. All right. So the high-level takeaways here is that each data set is unique, and it seems like the winning methods take great care of specializing their approach by tweaking hyperparameters, tweaking the learning rates to find what works best for each data set. So there is no one-size-fits-all solution. It also turns out that these multimodal large language models are better classifiers than they are object detectors. And we'll talk about that for things that I think the community should think about for future work. And maybe unsurprisingly, these ensembles win. So if you have infinite compute, you should sort of run all the models you have and take your best guess based on an aggregated set of your model's predictions. All right. So in future work, I think we as a community really need to think about this distinction between these specialist models like Grounding Dyno that are purpose-built and purpose-trained for the task of object detection, and our generalists like Quen3VL that not only solve the task of object detection, but are also great image captioners, are also great video understanding models. So right now it seems like there's this dichotomy between the two. And I have sort of two high-level thoughts on where this dichotomy might be coming from. So first, obviously, the training losses are very different. So for Quen, we have a next token prediction loss, whereas for Grounding Dyno, we're very precisely regressing your bounding box widths and heights. And importantly, a bounding box, a grounding Dyno style model is, I think, more discriminative in the sense that standard object detectors operate by first generating thousands of proposals. And the task of the object detector, or the final stages of an object detector, are to score each of these proposals and identify how we want to refine each of these boxes. And once we give a score, it's quite easy to then sort of threshold based on this score. So that's how your standard object detectors work. But Quen3VL, importantly, is sort of a generative approach. So we're generating tokens one at a time. And importantly, we're not actually assigning, or I should say, most popular generalist models, which are out today, don't assign confidence scores to their bounding boxes. So this sort of leads to these models being overly conservative with their set of predictions. So I think there's this interesting sort of split between these models. And I think, given the way the world is going, and sort of the industry is sort of pumping all their data and resources into making these generalist models better, I think there's a real opportunity for us as a community to really think about what the role of these specialist models are and how we might sort of bring some of the lessons that we've learned over the decades of building these object detectors to bear when we want to, train these models, train these these generalist models for more precise spatial localization tasks and spatial intelligence more broadly. All right, so I'd like to thank RoboFlow for helping sponsoring this challenge. It's because of folks like them and our partners in industry that help us raise prize money and get the community excited about challenges like this. So with that, I'll close this last section of the workshop on the challenge, and I'll briefly give 2 minutes of closing remarks. So I know everyone's hungry, wants to go to lunch, so I'll be very quick here. So all right. So workshop in review. It's been a wonderful half-day workshop here. We've had excellent talks from 7 speakers, and I just told you about our one challenge for this year. So these are the speakers, and we want to thank all of them for taking the time to share their latest work. The goals of the workshop, obviously, we want to connect people, we want to identify new opportunities, exchange ideas, and understand existing challenges. I think we've done all of that, and maybe some more. So the organizers of this workshop, I want to thank all the organizers that worked behind the scenes to help make this workshop a success. And importantly, I'd like to highlight Shu Kong, who is the lead organizer here. He's been running this workshop for 6 years now, and unfortunately, due to visa issues, he's never been able to be at this workshop in person, which I still find incredibly crazy. But he's still on Zoom. It's God knows what time in China, but he's making it work, and we thank Shu for his efforts. So the recording of this workshop in its entirety will be released later on YouTube in about 3 months. And I want to thank everyone for joining us today, and I hope to see you all at CVPR'27 in Seattle. Thank you, guys.
Listen, thanks again. This is great.
Thank you. Thank you.
One day she's gonna be.
It's good. Hopefully.
Have you ever met him at international conferences?
Yeah.
He's totally lost.
I know. It's crazy.
It's really crazy.
It's crazy. Thank you, Shu.
One day.
Yeah, one day. Hopefully. Shu, I'm going to sign off. Thank you. Cheers.